Hello students, and welcome back to your Rankplus JEE channel. My name is Durgesh Ma'am, your organic chemistry master teacher over here. In this session, we're going to complete top 100 GOC questions ever asked in your PYQs in your JEE Mains exam. Here we're going to cover each and every variety of questions ever asked from your GOC chapter. Very important chapter, because this chapter alone you can expect to get around 20 plus marks. So this chapter is kinda very important. You should have a very strong hold on it. And once again, reminding everyone that this chapter is actually very deceptive, in a sense that if you think that you know the entire theory about this chapter, but if you haven't done lots and lots of questions regarding this chapter, then you are not even 10% ready to take on the questions that actually come out of this chapter. So this session is extremely important. We are going to see various applications of GOC and how all the effects that you learn over here, resonance, mesomeric effect, your inductive effect, how are they used in calculating boiling point? How are they used in calculating your dipole moment? How are they used in knowing the pH value of a substance, or a pKa, or the acidity order, basicity order, or even how are they used to actually know about your keto-enol resonance? How is it used to know your aromaticity? So everything we're going to learn in this one session, and whatever I'm talking about like in the introduction of the video might seem haywire to you. What is ma'am actually saying? Like, what does any of it means? If you are also feeling the same way, that bacha definitely means that this session is very important for you. So please give me these 3 hours, and we're going to complete top 100 questions in just 3 hours, and just give me these 3 hours, right? So let us begin, and we are just going to focus on question solving without wasting any time once again, because we have lots of questions right now. So the very first question on the screen is, the increasing order of boiling point of the following compounds is. So what do you have to do? The very first thing, whenever such a question is asked, what you have to do is actually look at all the options given. So can you see all these options actually look the same? They have the same, like this is all a phenol group, and to the phenol group some other substituents are added. Okay. Now they are asking you about the boiling point. Now whenever they ask you about boiling point, actually depends on a lot of factors, but after seeing the options, I know that here the boiling point is actually dependent on the H bonding. What it is dependent on? On H bonding formation. So can you see the OH remains the same in all the 4 options, which means the OH group will definitely show H bonding. Remember, what is H bonding? Revise it. What is H bonding? H bonding only happens with 3 kinds of atoms, which is the strongest H bond happens with fluorine, followed by your oxygen, followed by your nitrogen. That is it. Only these 3 atoms actually show H bonding. No other atoms actually show you hydrogen bonding. Is this thing clear to you? Now, bacha, in these H bonding, can you see here NO2 group is attached? This NO2 group, the oxygen over here can show the hydrogen bonding. So here, ma'am, OH hydrogen bonding is present. Can you see the NH2 group? Here the NH2 group, here nitrogen once again can show the hydrogen bonding. So it will have once again a higher boiling point. Now OCH3 is present. This is kind of a ether group. This is actually a methoxide, but we can consider it as a kind of ether group, right? So remember one thing, whenever there are ethers present, ethers may the oxygen, in ethers the oxygen cannot show H bonding. Very important. Cannot show H bonding, but it has a dipole moment, right? It has a dipole moment. Why does it have a dipole moment? Can anyone tell me? It has a dipole moment because here oxygen is present, right? So why does it have a dipole moment? It has a dipole moment because the oxygen is attached to carbon, and we know the oxygen is more electronegative. Hence the dipole moment will be here, because both of the oxygens will actually attract the electrons towards itself. So it has some kind of dipole moment present here, right? So but it has a dipole moment, and always remember that boiling point is also directly proportional to your dipole moment, which is represented by mu. More the dipole moment, more will be the boiling point, right? So here in OCH3, dipole moment is present, right? Dipole moment is present. But in CH3 group, there is no dipole moment. Hence, the order of boiling point. What would be the order of boiling point? Hydrogen bonding, as we know, has a stronger effect on boiling point rather than a dipole moment itself. Hence, the OH nitro hydrogen bonding is much stronger. Hence, NO2 group will have a higher boiling point, followed by the NH2 group, which is the third option, followed by the dipole moment, which is the fourth option, followed by the first option. So, this would be the order of dipole moment. Understood? Here in dipole moment, I use the concept of hydrogen bonding. How did I use it? By actually evaluating the options. I saw that in some of the options, hydrogen bonding is present. In the other options, there is dipole moment can be shown. And here, there is no dipole moment and there is no H bonding even. Hence, this would be the order of boiling point. Therefore, these practice questions are very essential for you. Here, what you're going to learn through this session is actually how to tackle the options that are there in your exam, right? Because I know that you know about boiling point, you know about dipole moment, you know about hydrogen bonding, but how to actually involve all of these things in just one question and solve a simple boiling point question, right? Understood? Moving forward to the next question. The next kind of question, very, very popular, is the IUPAC naming. At least one question will definitely be there related to the IUPAC naming. So, please brush up your concept related to IUPAC, right? So, here, look at this compound over here. It is a very easy compound, right? In case you're very familiar with IUPAC, this is pretty easy. Pretty easy. So, can you see this is the priority group over here? As we know, COH is given the highest priority while solving questions. So, this carbon will get as the carbon number 1. Hence, this would be the carbon 2, this would be carbon 3 and this would be carbon 4. Now, whenever we are writing the IUPAC naming, remember another thing, which is we always write the name in alphabetical order, right? So, here at 4th position, there is bromo, there is 4-bromo, and then there is 2-methyl, right? 4-bromo, 2-methyl, and then there is cyclopentane, right? This is a cyclopentane group. So, here it would be cyclopentanoic acid. So, this is a 4-bromo 2-methyl cyclopentanoic acid is the answer over here, right? Now, the next question on your screen, which of the following has the shortest CCl bond? Now, once again, before solving this question, what you have to do, you have to just scan the kind of options given. Now, I'm not focusing on the question, I'm focusing on just the options. Can you see that here all of the options contain this group is similar in all of the 4 options, right? This group is similar. What is actually changing? The substituent attached to it. Can you see here a CH3 group is attached? So, ma'am, we know that CH3 group has a plus I effect, so I'm writing it over here. It actually increases the electron density and has a plus I effect. Here the NO2 group is actually a electron withdrawing group, right? It is taking away electrons from this species. Here OCH3 is once again a electron donating group. Here no such groups are added. Now, bacha, look at the options. Here can you see chlorine is added on all of these molecules. Now, chlorine has what kind of structure? Ma'am, chlorine has lone pair of electrons. So, I am just making the lone pair of electrons on chlorine like this, like this, like this, like this, like this, right? I am just making the lone pair of electrons on chlorine like this, right? Now, next thing, bacha, what will happen on chlorine? Now, bacha, can you see that here a electron withdrawing group is added, while on the rest of the 2 options, there is a electron donating group. Now, whenever NO2, because it is an electron withdrawing group, it's going to withdraw electrons from this entire species. So, what it is doing, it will actually grab this electron pair, and because of resonance, it will actually take the electron pairs towards itself. Can you see resonance can be shown because of the chlorine over here? Hence, because the electron withdrawing group is attached, this CCl bond would be the shortest bond over here, right? Would be the smallest bond, because NO2 group is strongly electron withdrawing. Hence, it will withdraw the electrons through resonance. Hence, this bond will actually get a double bond character like this, double bond, and then here it is CH, here it would be CH, here it will again be a double bond followed by a NO2 group like this. So, NO2 group is somewhat like this, here it would be the negative charge, here it would be like this, right? So, this Cl will actually get a positive charge as well as a double bond, right? Now, because this has a strong electron withdrawing group attached, this double bond would be the most prominent double bond, hence this would have the shortest bond over here. As we know that double bonds are shorter than your single bonds, right? Now, because of resonance present and because of the electron withdrawing nature of the NO2 group, this Cl will have the shortest bond amongst all these options. Understood? Is this concept clear to everyone? This is how you're going to apply it. Okay? Now, let's go to the next question. Next is once again JEE Mains 2024, this year's question. Look at this question. The correct sequence of acidic strength for the following aliphatic acids in the decreasing order is. So once again, so many acids are given to you. You have to just write their acidic strength in the decreasing order. As you know, what is the acidic strength? Acidic strength means the ability to actually give away the H plus ions, right? The ability to actually give away the H plus ions is the acidic strength. Right, bacha? This is the acidic strength. Now, bacha, what will happen? Now, ma'am, how will I know that which of these molecules will actually readily give away H plus and the other ones will not? Then, bacha, you have to know the stability of the anion that is left behind. Understanding this thing? So, what did I tell you? What compound is the most acidic, which easily gives away H plus, right? How am I accounting for the acidity? Acidity is accounted by which easily gives away the H plus ions. Now, ma'am, how will I know which one will easily give away H plus, which one will be difficult? Then, bacha, you have to tell by actually seeing the stability of this. So, the acidity is actually directly proportional to the stability of the anion formed, right? Stability of the anion formed. So, look at these, all the anions formed over here. It is CH3, CH2, C double bond O, O minus, right? So, this is one kind of anion formed over here. Now, I'll just write it over here so that it is much more clear. If I write down the anion, it is CH3, CH2, COO minus. This kind of anion is formed. Here once again CH3, CO minus anion is formed. Here CH3, CH2, CH2, CO minus anion is formed. So can you see, to all these anions plus I effect is shown by here. This is also showing plus I effect. This entire group is showing plus I effect. Here there is no plus I effect. See, if I am a negative charge, when will I be stable? If I am a negative charge, I will be stable when you are taking away electrons from me. If I am already negative, you are giving me more negative charge. That is actually rendering me to be less stable, right? If I have a negative charge on me, I will not be stable if you keep on continue to give me more negative charge, right? So here the most stable anion is actually this. Let me just write down here. It is A, this one is B, this one is C, and this one is D, right? So D will have the highest, D will have the highest stable your conjugate base or the anion, hence it is the most acidic, followed by your B, followed by your A, and followed by your C. So this is the order that is followed. I hope this is clear. Right? What did I say? How will you actually find out which one is more acidic? You will find out like, you will know the acidity order once you find out the one which easily gives away the H plus ions. And how do you know that? You know that by actually looking at the stability of the negative ion or the conjugate base formed after the H plus is removed, right? So here we can see if I am a negative charge, I'll be stable only if you take away electrons from me, not if you give me electrons. If you're giving me electrons, you're making me much more unstable. Hence, the most stable anion formed is D. Hence, it is the most acidic, followed by B, A and C. So, this is indeed the acidity order. What order is this? This is the acidity order. Right? Understood? Shall we move forward? Okay, bacha. This is the next question on your screen. Look at this question. The question is the correct arrangement for the decreasing order of electrophilic substitution for the above compounds is. Look at these compounds. These all are benzene rings and to which different kinds of groups are attached. And in the question you are asked to actually arrange them in the order of electrophilic substitution reaction. What are electrophilic substitution reaction? Whenever a electrophile which has a positive charge attacks on the benzene ring, those are electrophilic substitution reaction. See, if I am a positive charge, where will I attack the most? I will attack the most on the compound which has the highest amount of negative charge, right? Because opposite attract. So, this positive will be attracted to the ring which has the highest number of electrons in it. Remember one thing, I am going to teach you one very, very important thing. See, this is a benzene ring, right? What is benzene ring made up of? So many pi electrons. Can you see? There are so many pi bonds here. Pi bonds are actually electron rich, right? So here what happens whenever an electrophile is in the vicinity of the benzene ring, these pi electrons actually attack this positive charge, and what actually happens is something like this. What actually happens is you get a benzene ring and the electrophile attacks over here. So you get a substituted product, which means one of the hydrogen gets removed and instead of that hydrogen the electrophile gets added on the benzene ring, right? So what are actually attacking? These pi electrons are actually attacking on the benzene ring. So the more negative the benzene ring is, more easily it can attack the positive charge, right? So we have to look for the benzene ring which has the most negative charge on it. So look at the CH3. We know that ma'am CH3 group has a very good inductive effect. It is increasing electron density in the ring by the plus I effect, right? Plus I effect is doing what? Increasing electron density of the ring. Here there is no group. In third, once again, what kind of group is this? This is OCH3 group. Can you see that this can actually show resonance with the benzene ring, right? So I am writing here. It can show ma'am plus R effect, but along with it, it can also show minus I effect. Why? Because a very electronegative atom, oxygen, is directly attached to the benzene ring. So whenever a electronegative atom is directly attached to the benzene ring or any carbon chain, it will definitely show minus I effect. So understand these things. But here once again, as we know that resonance effect is much more dominating, so this will indeed behave as an electron donating group and not as an electron withdrawing group. Minus I effect is what? Which takes away electrons, that is a minus I effect. Plus I is which actually gives electron, that is a plus I effect. Is this thing clear to everyone? Right? Okay, let's move forward. Fourth option, you are having a group which is a CF3 group attached to the benzene ring. What kind of group is CF3 once again? CF3 is indeed a electron withdrawing group. What kind of group is this? This is a electron withdrawing group, right? CF3 is a kind of electron withdrawing group once again, right? So electron withdrawing group, it is decreasing the electron density in the ring. So here the correct order of arrangement of electrophilic substitution reaction. So this benzene ring is the most electronegative, right? So this one will have the highest amount of ESR reaction, which is electrophilic substitution reaction. This one is the most negative ring. It is the most electron rich ring. So it will show the highest electrophilic addition reaction, followed by your first one, followed by your second one, followed by your fourth one. Is this thing clear? Right? Here there is just plus I effect. Here there is a very strong electron withdrawing. This is a very strong. So you are decreasing the electron density on the ring. So it cannot attack the electrophile. Better than this is the normal benzene which has no group attached to it. So it will indeed act as a better nucleophile than this one. Understood? Shall we move forward? Right? Understood? This is showing plus I effect, this is showing plus R effect, this is showing electron withdrawing effect once again. Okay. Next question on the screen. Which of the following compounds will be the most easily attacked by the electrophile? Once again, there is a electrophile attack. What is a electrophile? Anything which has a positive charge on it is a electrophile. So, where the positive charge will attack? Positive charge will attack on the most negative species. So, let us identify the most negative species here. Here the OH group is present. It is showing plus R effect as well as minus I effect, right? Where plus R is actually the dominating effect. So, it is increasing electron density on the ring. It is activating the ring. I'll use another term for increasing electron density. Remember this thing. Whenever any group which is attached to the benzene ring has a electron donating effect. What kind of effect it has? It has a electron donating effect. Then bacha, we say that it is actually activating the ring. We use the term activating the ring. What term do we use? We use the term activating the ring, right? So whenever any group that is increasing electron density, right? What is activating the ring? Whenever we are increasing electron density increases, then we use the term activating, right? So we are going to see this term a lot more in this chapter, right? Okay, now here the chlorine group once again. The chlorine group is actually electron withdrawing group. It is actually a deactivating, weakly deactivating group. It is a weakly deactivating group. Understand this thing, right? Once again, there is CH3 present over here. What kind of group is CH3? CH3 actually shows your plus I effect. What kind of effect does it show? It shows plus I effect, CH3, right? Now, which of the following compounds will be most easily attacked by an electrophile? So, can you see in the A option, it is showing a positive resonance effect. Hence, A will show the most positive, is the most electron rich, followed by your D ring, followed by your actually C ring, followed by your B ring. Because in B, once again, there is a feeble, weakly deactivating group. It actually decreases electron density on the ring, right? It actually is decreasing the electron density on the ring because it has a much higher minus I effect. What does it have? It has a much higher minus I, which is also called the inductive effect, right? It has a much higher minus I effect. Is this thing clear to everyone? Right? So this is going to be the order of attack of the electrophile. Most negative ring is the OH ring because it is showing the plus R effect, followed by the D plus I effect, followed by your C. It has no effect, followed by the minus I effect. Right? Easy? Okay. Let's move forward to the next question. Once again, there is another question of the correct order of the reactivity in the electrophilic substitution reactions. I hope you will be able to do it. This is based on the similar methods that we just used right now. Right, once again, electrophilic, some positive charge will have to attack. Here CH3 group is there, it is showing plus I effect. Here OH group is there. Once again, it is showing plus R effect. And here this NO2 group is present, it is showing the electron withdrawing. It is a electron withdrawing group. Now the positive will attack on the ring which has the highest electron density, which is actually present in the third option, followed by the second option, followed by the first option, followed by the fourth option. I hope this thing is clear because we've practiced it enough number of times up till now, right? We've practiced it enough number of times, right? Moving forward. Next question is another variety of question from the inductive effect. The ascending acidity order of the following hydrogen atom is. You have to tell me the acidity order of the following hydrogen atom. Remember one thing, whenever look at the options. What is the first thing I taught you? To always scan the variety of options given. Can you see? Here the hydrogen is attached to a triple bonded carbon, here to a double bonded, here to a normal single bonded carbon, and here to once again a normal single bonded carbon, right? Now what is the thing that I taught you? The thing that I taught you is, remember one thing, for the acidity order, here different kind of hybridizations are also given away, right? The triple bonded carbon is actually sp hybridized, right? So I'm writing the hybridizations over here. So these are the three varieties of hybridization, sp3, sp2 and se. So as you are going down, can you see that the percentage S character is actually increasing, right? The percentage S character is increasing, which means that the electronegativity is increasing. What is happening to the electronegativity? It is increasing. What is meant by that? Remember the periodic table in your head now. Which is the most electronegative element in the periodic table? Isn't it fluorine? Isn't it oxygen? Right? So after, like, as you are moving along a period, the electronegativity is actually increasing, right? So what do you know about these electronegative elements? Have you ever seen fluorine with a negative charge? Yes, ma'am, it is very, very common. But have you ever seen fluorine with a positive charge on it? No, never. Why? Because a positive charge on a very electronegative atom is very, very unstable. What kind it is? It is very, very unstable. A negative charge is stable on an electronegative element. Is this thing clear? Now, bacha, for checking the acidity, what is the first thing that we actually look for? We look for that what is acidity? That the hydrogen actually leaves easily. So I'm just removing the hydrogens marked over here, over here, over here. After removing the hydrogen or the H plus, what remains is a negative charge over here. Now can you see that this carbon is sp hybridized, which is the most electronegative carbon. Hence the negative charge is very stable over here. Therefore this is what? This is more acidic, right? So what is the acidic compound? We have already discussed the acidity order, right? We have already discussed about the acidity order, right? The acidity is indeed directly proportional to what it is directly proportional to. The acidity order is directly proportional to the stability of the anion formed, right? More stable is the anion, more is the acidity. So here the anion formed has a negative charge on the sp hybridized carbon, right? Therefore, this one is the most acidic in nature. This sp hybridized is indeed the most acidic in nature, right? Here, if you are comparing between the sp2, sp3 and sp hybridized carbons. So, once again, this is very stable, followed by the sp2 carbon. This carbon is indeed sp2. Now, can you see these carbons over here? This is sp3 and this also is sp3 hybridized. Now, look at this hydrogen over here. This hydrogen is actually attached to the kind of carbon. Now, if I remove this over here, what will remain here? A negative charge, right? A negative charge will remain here. Now, can you see that too many of the plus I groups are actually added on this negative charge? I'm already negative and you are increasing my negativity by actually adding more and more plus I effects on me. So, I actually become much more unstable. If I'm negative, see, none of the charges are stable. Neither a negative charge nor a positive charge. What is actually stable in life is a neutral molecule. So, whenever you are too much angry, it is not stable. Whenever you are too much sweet, it is also not good for you. So, you have to find a balance in life. So, the balance for the molecules is a neutral molecule, right? So, the neutral molecules are much more stable. So, if I am negative, you are increasing negativity on me, you are decreasing my stability. So, this is very, very unstable. But here there is just one plus I effect, a negative charge will be formed over here. But here there is just one plus I effect. So, here the stability of the negative charge is not that much affected as compared to the C counterpart, right? So, here the most stable anion is indeed A, followed by B, followed by D, followed by C. So, this is the acidity order, right? The negative charge is more stable on the sp hybridized carbon followed by the sp2. And here we have to check like the plus I effect is actually decreasing the stability of the negative charge over here, right? So this is the acidity order. Understood? Easy. Moving forward to the next question. This is JEE Main's 2022 question. Look at this question. Arrange the following in increasing order of reactivity towards nitration. What is the nitration reaction? Nitration reaction happens in the presence of the reagent HNO3 as well as H2SO4, right? And what is the electrophile here? The electrophile formed is actually NO2 plus ion. So can you see a electrophile is formed? Hence, if a positive species has to attack, then it will attack the kind of molecule which will have the highest negative charge on it, right? So these were all the options given in your JEE exams. Can you look at the options? Most of these are actually what? Most of these are common names of the compounds given in the NCERT. So that's why I've included this question. This is once again an electrophile inducing question, but I had to include in order to make you remember the importance of common names that you cannot skip, especially if they're given in your NCERT. What is paraxylene? What is bromobenzene? What is mesitylene? What is nitrobenzene? And what is your benzene, right? You have to know the structures of all these compounds. Now this is, take it as a homework question, right? Because the method is similar as what I've taught you for the electrophile, right? A positive charge will attack the ring on which the most negative, or the ring which has the most negative charge on it. So you just have to find out which ring has the most negative charge by looking at the substituents attached to it. This is a homework question, so that you actually go through your NCERT and look at all the common names given in NCERT. Take it as a task, right? So take a screenshot of it. Once again, a 2022 question, right? Next question on your screen for the JEE Mains 2024. Look at this question. The descending order of acidity of the following carboxylic acid is. So we have already done one carboxylic acid acidity order. This is another kind. So can you see here fluorine group is attached. Once again, what is the acidity order? Scanning the options. After scanning the options, what I can see is, ma'am, all of these are actually carboxylic acids. Okay. So here, because I have to check the acidity, I have to actually remove the H plus ions from it. So I have removed the H plus ions. Now what is left behind is actually a negative charge, negative charge, negative charge. So a negative charge will be left behind on it. Now I have to check the stability of the negative charge. I have to check what kind of substituents are added. So can you see here CH3? It is just showing the plus I effect. And here once again this is showing a very, very strong minus I effect. This is also showing, this chlorine is showing minus I effect. This fluorine is also showing minus I effect. This bromine is also showing minus I effect. Now when we are comparing the inductive effect order, you must know that the strength of minus I effect, fluorine has the strongest, followed by chlorine, followed by bromine, and followed by iodine. So whenever we are comparing the minus I effect of the halogens, this is the order followed. Fluorines have the highest electron withdrawing effect, right? So can you see there how many fluorines are added? Fluorines, 3 fluorines are added on here. So that is why B will have the most acidic compound, followed by your D, followed by your C, followed by your E, and followed by your A. So this would be the acidity order. This is the acidity order. Why is this the acidity order? Acidity order means what? The compound which easily gives away H plus. Now ma'am, how will I know which compound will easily give away at H plus? I will know in a sense. I will know in a sense that I have to look at the stability of the anions left behind after the H plus has left. So I have to look at the stability of the anions. More stable the anion, more acidic is the compound. Now I know if I have a negative charge, I need groups which are actually taking away electrons from me. As I know, fluorine has the strongest minus I effect, which is the electron withdrawing effect. It will have the stablest negative charge, followed by D, followed by C, E, and your A. Right? Easy acidity order. This is how you will tell. So all these questions are very, very good questions. Now look at, now we've entered another territory of the resonating, of resonance. So we have completed all the questions that can be asked from the inductive effect. Now we are entering another territory of resonance. Now bacha, the first question that is from the theory asked in your JEE Mains 2024 exam. Look at this question. What effect is observed in which interaction occurs between pi bond and lone pair of electrons on adjacent atoms? What effect is observed in which interaction occurs between pi bonds and lone pair of electrons on adjacent atoms? So very interesting question. Always remember this thing. In inductive effect, what happens, whether plus I or minus I effect? In inductive effect, there is just involvement of sigma electrons, right? In resonance effect, there is involvement of sigma plus pi electrons, right? And in the hyperconjugation effect, there is involvement of what kind of electrons? There is, once again, there is involvement of, in resonance, bacha, what happens? I'm really sorry. In resonance, there is involvement of just pi electrons, and in hyperconjugation, there is involvement of sigma plus pi electrons, right? So this is the order that is followed, right? So in inductive effect, just sigma electrons are involved. In resonance, just pi electrons are involved, pi electrons or lone pairs, one and the same. And in your hyperconjugation, sigma and pi electrons are involved. The question is, you have to tell me which effect observes the interaction between pi bonds and lone pair. As we know that if such kind of group is there, C double bond O, it will definitely observe a resonating effect, right? So between pi bond and lone pair, you only observe the resonance effect, right? Is this thing clear? So in inductive effect, only sigma electrons are involved. In resonance, pi, and in hyperconjugation, sigma plus pi electrons are involved, right? Next question from your JEE Mains 2023, resonance of carbonate ion is. So these are all the resonating structures possible for the CO3 2- ions, right? Which of the following is correct? So you must know a few things about the resonating structure. So whenever I draw the resonating structures, bacha, which of these structure is the most is actually found in real life, right? That could be a question. So remember one thing, all of these resonating structures are imaginary or they are hypothetical. None of these structures actually exist. What actually exists is just a resonance hybrid of all the resonating structure. For example, what actually exists from this compound would be something like this, like all the 3 oxygens will have a partial double bond character, as well as all of the 3 oxygen will have a negative charge on it. So what actually exists is a resonance hybrid of all these 3 resonating structures. None of these structures actually exist. These are all hypothetical. Whenever, okay, remember, you can remember this by actually the example of benzene. Benzene you can draw like this, or you can draw a resonating structure of benzene like this, right? Here the bond moved here, the bond moved here, the bond moved here, right? You can draw the resonating structure like this. This can be done. Now, bacha, which of these structures actually exist in real life? So your answer would be that, ma'am, actually a resonance hybrid in which all of these electrons, all of these bonds actually has a partial double bond character on it actually exist, right? Like this. So this compound actually exists. None of the other compounds actually exists, right? So which of the following is true? It is possible to identify each structure individually by some physical or chemical method. It is asking, is it possible to identify any of these structures? The answer is no, it is not possible. So which of the following is true? This is definitely not true, right? Because these structures are hypothetical. We have made them in our head. What actually exists is just the resonance hybrid. Next is, all these structures are in dynamic equilibrium with each other. False statement, these structures do not even exist to be in dynamic equilibrium with each other, right? They are not in dynamic equilibrium. False statement, each structure exists for equal amount of time. No, these structures do not even exist. Next is, carbonate has a single structure that is resonance hybrid of the above three structures. Absolutely correct statement. This CO3 minus just has this structure where all of these oxygen has a negative charge and all of the oxygens has a double bond character on them. Understood this thing? So all of these statements are wrong. Only the last one is the correct statement. Right? I hope I'm making my point extremely clear to you guys. Moving forward to the next thing, which will undergo deprotonation most readily in basic medium. This is once again a very interesting kind of question. Deprotonation. What do you understand by the term? Deprotonation. What is the meaning of proton? Means H plus. What is deprotonation? Which means you are removing proton. Removing proton means what? Acidity order, isn't it? What is the acidity order? Acidity order means which easily gives away H plus. Here also, they've just used a different term. Instead of acidity, they've used deprotonation. So they play on these terms, and you don't have to actually get blindsided with these terms or get very scared. These terms mean one and the same thing, which means it is asking about the acidity order strength. So they've given you 3 compounds and they've asked you which will most readily undergo deprotonation in basic medium. Now understand what is a basic medium. A basic medium, for example, has a OH negative ion on it. So whenever a base is present, right? So what is the dharma of a base? Everyone has a dharma and a karma, right? So dharma of the base is to abstract the H plus ion, right? And always remember this thing. Whenever the base is present, it will always abstract H plus ion, and also the group which are very good leaving groups are present. If any good leaving group is present, it will also abstract that. So I'm not including it over here, but you should know it after when we are in the next lesson. I'm going to teach you how to actually what kind of most repeated reagents are asked in your exam. So once again, we will encounter bases over there, and there we will see that what is the dharma of a base. The dharma of a base is to abstract the H plus and also the very good leaving groups. Understanding this thing, so it also abstracts the leaving groups from it. Okay, so this is a base and it abstracts the H plus. Okay, so here which will easily give away H plus. Once again, the same dharma of the acidity is followed over here, right? So what is the purpose of acidity? We already know the more acidic compounds are those which have a more stable anion, right? More stable the anion, or the anion is actually called a conjugate base left behind after the H plus is gone. Now I want to teach you, is this thing clear? So we are going to clear so many concepts using each questions, right? So as I cleared concepts of resonating structures to you, right? We are also going to clear concepts of what is the stability of resonating structures. We are also going to go in that direction as well. But focus on each and everything that I'm trying to teach you in these PYQs. Also remember one thing, whenever you're encountering PYQs, right? So these PYQs are important in a sense that all these whatever groups are added, right? So you have seen like these kind of groups are asked in your exam, right? Or boiling point is, or how the boiling points are asked, or how the questions of acidity are asked. So this is actually giving you a very good hint on the kind of questions that you should expect in your JEE Mains January attempt 2025 exams, right? So once again, coming back to the question here, okay, you have to calculate the acidity order because we are obviously talking about deprotonation, which actually is the same thing as the acidity order, right? Which is giving away H plus. Now, the acidity order is directly dependent on more stability, anion or the conjugate bases. Another thing that you can learn from this question is look at the group that is attached to it. Can you see a carbonyl group is attached? So what I'm teaching you right now, whenever any group which has a multiple bond attached to it, can you see a multiple bond is there? So whenever any group with a multiple bond attached to it is attached, that group will always act as a very good electron withdrawing group. What kind of group? Electron withdrawing group. and the hydrogens attached next to the electron withdrawing group, for example, this hydrogen becomes very, very acidic. Why? Because this is a very strong electron withdrawing group. So whenever the H plus leaves from here, what can happen? After the H plus leaves, a negative charge is formed behind. Now this negative charge can actually show resonance with this multiple bond present over here. Hence, this hydrogen becomes acidic because the anion left behind is stabilized by the resonance. So you don't have to remember all this story behind it. I mean, the story is good to know. But what is the identification mark that you have to look for? You have to look for whenever a multiple bonded group is there. Can you see a multiple bonded group? Hence, these groups will actually make the hydrogens just right next to them. Can you see this hydrogen? Can you see this hydrogen over here? Can you see this hydrogen over here? So they will render this hydrogen very, very acidic. So this hydrogen becomes acidic because a negative charged form over here will be stabilized by resonance. Is this thing clear? Whenever an electron withdrawing group is attached, how to identify electron withdrawing group? Whenever it has a multiple bond attached to it. Very strong electron withdrawing group, the hydrogen next to it will be acidic. Now, amongst these three options, so ma'am, what you are saying is, all of these three groups will render a very, very acidic hydrogen. No. Look at the substituents attached on these groups. So now I'm talking about the next thing that you should know. So I'm rubbing this, right? So I'm rubbing this. I hope this thing is clear with everyone. So we are moving into the next direction of this question. Now look at over here. I am just taking the example of the B option. I'm drawing the B option over here. So the B option looks like this. This is double bond O. This is here. This is here. This is double bond O. Here it is OME. And here once again there is OME. Right? So look at this OME over here. This OME has a lot of lone pair here. Has a lot of lone pairs here. Right? So here what this O will do, bacha? This O can actually show resonance like this, right? This O can actually show resonance like this, and this O can actually show resonance like this, right? Right? So what is happening? What is happening? I will just correct myself a little bit. I just want to draw this arrow over here. I just want to draw this arrow over here, right? Can you see even these electrons are participating in resonance with this double bond? Right? Now bacha, if a hydrogen from here leaves and a negative charge is left behind, now what will happen to the negative charge? This negative charge is now in competition with these lone pair of electrons which are already participating in resonance. So can you see this negative charge will get lesser chances to participate in resonance. But look at the A option. The A option looks like this. The A option has no competition. Now, if a negative charge comes over here, this negative charge can resonate here. This negative charge can resonate here without any competition. Hence, this hydrogen is the most acidic hydrogen because this negative charge is stabilized by two of the resonating structures, while here there is competition present. Hence, this negative charge is not that stable. Due to the competition, it will get lesser chance to participate in resonance. Hence, it will not be stable. Similarly, in this case, once again, due to this oxygen, this will also participate in resonance. Hence, this negative charge formed over here will not be that much stable. Hence, the most stable negative charge is A only. So, therefore, the most readily deprotonation will actually happen in the A option and not anywhere else. Is this clear to everyone? Right? So, once again, see, all these questions asked in a JEE Mains exam actually requires a lot of head hurting, a lot of efforts to solve them. But that's what this session is all about. In order to reduce that head hurting in your exam, you have to do like at least 500 plus questions, which we'll definitely do in this PYQ series of your organic chemistry, so that on the main day your head remains intact and you can apply your brains in other maths questions or your physics questions, right? We will make your chemistry part easier for you, right? Okay. Understood? Let's move on to the next question here. Which of the following has the highest acidic hydrogen? Once again, look at the options, scan the options. Can you see that here once again CO group is present. Here CO group is present, CO group is present. Here once again CO group is present. Here once again CO group is present. So here, ma'am, in all the position there is a C double bond O group, and as you told us, the C double bond O group is a good electron withdrawing group, and hence the hydrogens next to it are more acidic hydrogens. But understand one thing, here in the fourth option, look at the fourth option. Here the CH2 group is actually in between the two electron withdrawing groups. Hence, this hydrogen is indeed the most acidic hydrogen. Is this thing clear? Because the two groups present over here, now this negative charge, now whenever the hydrogen leaves from here, so it will form a structure somewhat like this, double bond O. Here there is double bond O, and here there is double bond O. So here when this hydrogen leaves, the negative charge is stabilized by this structure as well, by the resonance shown by here as well, right? And this kind of resonance is not possible anywhere else. Here's just one double bond O is there. So even if a negative charge comes over here, it can show resonance with just one CO group. Here also once again, if this negative becomes, then this can show resonance with just one CO group because the other one is too far away. Here once again with this CO group, it can just show resonance with just one oxygen because the other one is too far away, right? So the most acidic hydrogen is this one because the negative charge is stabilized by two CO groups. Hence, this is the most acidic hydrogen. So whenever any hydrogen is present between two electron withdrawing groups, right? So what is the takeaway from this question? Whenever a hydrogen is present between two strong electron withdrawing groups, then that hydrogen is very acidic because the negative charge left behind is stabilized by the electron withdrawing groups, right? So what we have learned from here that the COO group is a very, very good electron withdrawing group. Hence, what is the function of electron withdrawing group? To stabilize the negative charge. To stabilize the negative charge, right? To stabilize the negative charge. Understood? Let's move forward. Next is the correct stability order of the following resonance structures are given over here. So what they have given to you in a question is a molecule which looks like this. I'm just drawing the molecule over here, CH3, CH, and here it is a double bond. Here is once again a CH, and a C double bond OH group is present over here, right? This kind of group is present, and now what they've asked you is to write the stability of the resonating structures, right? So look over here once again. Okay? And now they've given you three structures and you have to tell the stability of the resonating structures. And this structure is not included in telling the stability. Only 1, 2, 3 structures are given. Now, bacha, for telling the stability of resonating structure, there are few rules and you have to obey these rules in the order that I'm telling you. The first rule is that neutral structures are more stable. Neutral structures are more stable structure. This is the very first top priority rule. The second, there are just 3 rules. The second rule is more the number of bonds. More the number of bonds, more stable is the structure. More stable is the structure. Now, ma'am, what does that mean? More number of bonds actually correspond to, which means that the octet of each of the atoms present in the resonating structure is actually complete. You will encounter such questions as well. We'll see such examples. But I've reduced, like, how will you count the octet of each and every atom present here? It will be time consuming, right? For most students, it must be even difficult even. So what you have to do, you just have to count the number of bonds that you can see in the structure given. So can you see how, so all these structures with the very first point, can you see, is there any neutral structure given? Is there any neutral structure? Yes, ma'am. This structure is actually looking neutral to me because this is neutral. This will definitely be the most stable structure. So the third structure will be the most stable because it is neutral. The second point is you have to look for, now here it has a positive charge and here they also have positive negative charges. These are charge structures. Now here, which one is more stable? Once again, count the number of bonds. Can you count? Here it is 1 bond, 2 bond, 3, 4, 5, 6. 6 bonds I can see, right? Whatever bonds you can see with your naked eye, just count those bonds, that is it. So can you see there are 6 bonds present, and here once again 1, 2, 3, 4, 5, 6. Once again 6 bonds are present over here. So ma'am, the number of bonds looks similar to me. Now because we have counted the similar number of bonds, which means what I will tell you more examples why have I asked you to count the number of bonds. Just trust your teacher on this, bacha, right? So what I'm actually doing by counting the number of bonds, I'm actually checking whether all of the octets of each of the atom present in the structure is complete. Now because they have the same number of bonds, which means that I cannot distinguish between the using the second rule. The third rule and the last rule is that the negative charge, not the change, it is actually the negative charge, more stable on more electronegative atom, Is this thing clear? Negative charge is more stable on the more electronegative atom, right? For example, look at the structure. Here the negative charge is present on oxygen. Hence the second structure is more stable, followed by the first structure. So this is the stability of the resonating structures asked in this question. Third followed by second followed by first, right? Why is this the stability order? Because neutral structures are more stable, followed by the structures which have a complete octet present in them, followed by the structures which have a negative charge on the more electronegative atom. Here the negative charge is on oxygen, while here the negative charge is actually on the carbon atom. Carbon is less electronegative, so therefore negative charge is more stable on the oxygen atom. So this structure is more stable. So these are just the 3 points. Using them you can calculate the stability of any resonating structures asked in your exam, right? Let's move on to the next question asked this year. The functional group that shows negative resonance effect is negative resonance, which means what? The functional group which shows minus R effect. Now, the best trick to recognize which shows the minus R or the plus R effect is, beta, the plus R effect is always shown by the groups which has a lone pair of electron attached to them. Whenever anything has a lone pair directly attached to the atom or the ring, it will definitely show what? Plus R effect. Minus R, how to identify? Whenever any atom directly attached has a multiple bond on it. What does it have? A multiple bond present. A multiple bond present directly attached to the benzene ring or to the atom, then that is a minus R effect. Now can you see NH3 over here has a lone pair, so it will show plus R effect. OH once again has a lone pair, will show plus R effect. COH actually looks like this, C double bond O, OH. Can everyone see? So the C double bond O group acts as an electron withdrawing group. Hence, it will show a minus R effect. OR once again has a lone pair of electrons, so it will show plus R effect. So the minus R is shown by just the third option. Easy? Understood? Moving forward. Next is, which of the following is the strongest Bronsted base? JEE Mains 2024 question. Which is the strongest Bronsted base? Very, very important. Now, bacha, what is a Bronsted base? This is over here, this is over here, but this is over here. I'm just drawing the lone pair of electrons. So, okay, remember, okay, these are few advices I want to give you when you are attempting your organic chemistry paper. Always draw the lone pairs existing on halogens, existing on oxygens, existing on the, okay, I'll not say this, I'll say always draw the lone pairs existing on the halogen family, existing on the oxygen family, existing on the nitrogen family, because it will make, like whenever you draw the lone pairs, half of the questions start becoming visible to you, right? So now the half of the effects start becoming visible to you, and that should be the way to go, right? Here they've asked you which of the following is the strongest Bronsted base. What is a strong Bronsted base? Beta, a strong Bronsted base is which easily gives away which easily gives away electron pairs, right? Which easily give away electron pairs is a strong Bronsted base, right? It has to give away electrons. Now look at this aniline over here. Can you see, ma'am, this aniline will actually participate in resonance with the benzene ring. Hence, these lone pairs are not available to donate because these lone pairs are participating in resonance. So this is not a good base. Look at this option. So I'll just mark them as A option, this one as a B option, this one as a C option, and this one as a D option, right? Now look at the B option. Can you see that the B option here, the lone pairs once again are participating in resonance, and after participating in resonance, they are actually becoming a 6pi electron system. Can you see? 2 electrons from here, 2 electrons from this pi bond, 2 electrons from this pi bond. Total 6 electrons. Hence, these 6 electrons are participating in actually 6pi electron system is what kind of system? Aromatic system. Now, because these electrons are participating in aromaticity, they are not at all available for donation. So, these are not, do not donate electrons. Do not donate electrons ever because they're participating in aromaticity, they're becoming more and more stable. Why will I donate my electrons? They will not donate. Next is C option. Here there is a NH group over here. Once again, this NH group can participate in resonance like this, right? This NH electrons can also participate in this benzene ring. So these electrons are participating in resonance with 2 benzene ring attached. Hence, these electrons are not at all available for donation. So, these will donate very, very less kind of electrons. Now, look at the D option. Here, these electrons are available to donate. They can donate the electrons much easily. Why? Because these electrons are also attached to the CH3 groups, which are actually the plus I groups. What kind of groups are they? Plus I, which is the electron donating groups, right? So, they are attached to the electron donating groups over here. Hence, they are increasing the electron density on the nitrogen atom, right? Because they are increasing the electron density on the nitrogen atom. Hence, bacha, they actually become good bases. So, this is a very good base. See, how am I a good base if I have too many electrons and also species are added on me which are showing plus I effect, increasing electron density on me. So, I can donate much more electrons. So, the best base is indeed the D base followed by your A base, right? Even though they are participating in resonance, but here these electrons are participating in twice the number of resonating structure, then followed by your C, then followed by your B. So, this is the order. Now, bacha, because the B electrons are participating in aromaticity, they will be least available for any donation. They will not be available for any donation. Here in resonance, we can compare these are much more available as compared to this than as compared to the B counterpart. Is this clear? A base is something which donates the electrons easily. An acid is something which donates H plus easily. So, whenever we are looking for the acidity or the basicity order, we are looking at these things which I just explained to you. Is this clear to everyone? The strongest Bronsted base which easily gives away electrons, which will be the D counterpart, then followed by the A, followed by the C, followed by the B. So, these order you have to remember, they can ask the order in any format. So, every order I am telling you is very, very crucial, very, very important. Next question on the screen, which of the following carbocation is the most stable carbocation? So, you have to tell which of the following is the most stable carbocation, right? Now, bacha, look, if I am a carbocation, how will I be stable, right? So, the more resonating structures I have, more stable will be the carbocation. So, look at over here. So, all of these groups, now what do you have to do? So, whenever any question is asked in especially your organic chemistry exam, remember that you have to scan the options. So, can you see all of these options look exactly the same? What is actually changing? Here it is made up of just 1, 2, 3 carbon atoms. Here it is made up of 1, 2, 3, 4, 5 carbon atoms. And here once again 1, 2, 3, 4, 4 carbon atoms. Here once again 1, 2, 3, 4, 5, 6 carbon atoms, right? So what they're changing is just the number of carbon atoms. So can you see once again in every option the positive charge can actually show resonance. It is participating in resonance over here also, over here also, here also, and here also, right? How is it participating in D option? Let me write. In D option, ma'am, this positive, because I have to look at the stability of the positive charge, right? So this stability of the positive charge, I can write here, it is OCH3, right? So here the positive charge, the double bond can move over here. Now if the double bond moves over here, the positive charge comes here, and the next double bond, what does this look like? This one pahar followed by another followed by here, right? Now here bacha, this double bond actually moves here, so the positive charge comes here. There is another double bond over here. Now what will happen once again? Here once again the structure that I can draw looks like this and this, right? The double bond is here followed by this double bond once again can move over here due to resonance, right? Double bond followed by a single bond and a positive charge are in resonance. Okay, you have to remember these things. This will again show resonance, so the positive charge will come here, and here there is the OCH3 atom. Remember one thing, whenever a positive charge is right next to a atom which has what do you say, lone pairs to them, then that bacha is a very, very stable positive charge. So this positive charge becomes very stable. Remember this thing. Whenever a carbocation is right next to an atom which has a lot of lone pair of electrons, then that positive charge is very stable. So I've drawn the resonating structure in the D option. Let us also draw the resonating structure in the C option. The C option, what will happen? Once again, this will move over here. So it will form 1, 2, 3. So this will come over here, the positive charge will come over here, and here is the OCH3 molecule, right? So here there is just 1 and 2 resonating structures. Here there were 1 and 2 and 3 resonating structures present. Can everyone see? 3 resonating structures bacha were present over here. Here there are just 2 resonating structures. Now if I try to draw the resonating structure over here, how many resonating structures would be present? 1, 2, 3, 4. So this double bond will actually move over here, right? And here is the OCH3 part. So that when the double bond moves over here, the positive charge actually comes over here, and there is a double bond over here, right? Now once again I can draw the resonating structure. This double bond will move over here, right? So here once again 1, 2, 3, 4. It will come over here. This double bond will come over here. The positive charge comes over here, and here is the OCH3 group. Now once again in the B option, in the B option we again have 3 resonating structures. Can everyone see that? We again have 3 resonating structures, but the positive charge is not right next to the atom which has a lone pair of electrons. Here also the positive charge is not right next to the atom which has a lone pair of electron, but in the D option the positive charge comes right next to the atom which has a lone pair of electron. This has an extra stability because once again it can show a resonating structure by like this. Here 1, 2, 3, 4, right? Here this, and here it is this, and here it is. Once again OCH3 positive can be formed like this. Can everyone see that? Right? So once again another resonating structure is possible. So whenever a positive charge is right next to a lone pair, it can again show a resonating structure, hence rendering it much more stable. So therefore the D option is much more stable, as you can already see that the A option will definitely have much less resonating structures, right? So the most stable carbocation form will be the D carbocation because it has the highest number of resonating structures. So whenever we are talking about stability of anything, remember one thing, more the resonating structures, more stable would be the compound. More the hyperconjugating structures, more stable will be the compound. And if the compound is becoming aromatic, it will definitely be the most stable. So whenever we are talking about stability, the most stable compounds are the aromatic compounds, followed by the compounds which have more number of resonating structures or the, okay, okay, and followed by the compounds which have more hyperconjugating structures. Right? Understood? Next question. Next question is, which among the following resonating structures are not correct? Very, very good question once again. Which of the following resonating structures are not correct? So can you see the very, very first option? Here, ma'am. So whenever I'm scanning the options, while looking at the very first option, I can see that, ma'am, here the nitrogen actually has the positive charge, and once again, even this carbon has a positive charge, right? So two positive charges, bacha, can never be right next to each other. They are not stable at all. So this definitely is not correct at all. See, right next to a positive charge, there should be a negative charge. This is not stable at all, right? Now, if I look at the very rest of the structures once again, look at the three options. The third option here, the nitrogen has 1, 2, 3, 4, 5 bonds attached to it, right? Nitrogen cannot form more than 4 bonds. Always remember that, right? So here nitrogen is forming 5 bonds, which is not possible at all. So this is also a incorrect structure. So both of these structures are actually incorrect. And if you look at the other structures, I can form all these structures, a positive, negative, positive, negative, positive. This can definitely be formed. Even this structure can be formed. But your first and third structures are not at all possible, which means two similar charges cannot be right next to each other. And similarly, your second period elements. So whenever I'm talking about second period elements, right? So second period elements are what? Second period elements are your carbon, nitrogen, oxygens, fluorine. These cannot have more than 4 bonds forming out of them. Maximum bonds they can have are 4 bonds, right? Second period elements. Next, which of the following compounds does not exhibit resonance? Very, very good question once again. Does not exhibit resonance, right? For resonance to be shown, okay, I'm just going to tell you all the species that can show resonance. Remember this one thing. There is one logic, and that logic is enough to determine whether it will show resonance or not in any question, right? The logic is there should be a double bond, right? Followed by a single bond, for example, carbon and carbon, and then a single bond. And to that single bond, there can be a lone pair, right? So this will show resonance. A double bond, single bond, and a lone pair will show resonance. Similarly, a double bond and followed by a single bond, followed by a negative charge will show resonance. This will also show. This will also show. A double bond followed by a single bond and a positive charge will show resonance in the opposite direction, right? A double bond followed by a single bond and a free radical will once again show resonance like this. This will move over here, right? So this will also show resonance. So these are the only varieties, and also again another thing which is a carbocation followed by anything which has a lone pair of electrons like this. This will also show your resonance, right? So these are the 5 conditions which can show resonance, and none other conditions exist. So this is the perfect way: double bond, single bond, lone pair, a double bond, single bond, negative charge, a double bond, single bond, positive charge, a double bond, single bond, free radical, and a lone pair and a single bond and a carbocation will definitely show resonance. So these are all the types which can show resonance. Now look at over here. Can you see that here there is a OCH3, oxygen has a lone pair. So I'm writing it much more clearly. This is something like this: CH3, CH2O, and here it is CH double bond CH2, and here it is the lone pair. Can everyone see there is a double bond followed by a single bond and a lone pair will definitely show resonance in this direction, right? In this direction, there is no other direction can show. This will definitely show resonance. This will show resonance here once again. Can you see there is a benzene ring. Benzene ring has pi electrons in them, and a CH2 and a OH. Oxygen has lone pair of electrons. Now, can you see that lone pair followed by a single bond again has a single bond over here? So there is no double bond. So here this cannot show resonating structure. What is this? This is benzyl alcohol. Cannot show your resonating structure or your resonance. ठीक है. And next is your CH3, CH2, CONH2. So CONH2 has a structure like this. CONH2 has a structure like this. So the electrons move over here and this move over here. And this will show a resonating structure like this, COOO minus followed by double bond NH2 plus, right? So this will also show resonance because there is a double bond, single bond and a lone pair. Will definitely show resonance. Similarly, look at the fourth option. The fourth option will also not show. Here there is CH double bond CH2, CH, then again a single bond CH2 and a NH2 group over here. So there is a lone pair, single bond and then once again a single bond. So this will also not show resonance. So the correct option is fourth will also not show resonance. So second and fourth option will not show resonance. Rest of them will show resonance. I hope this thing is clear to everyone. Right? All these questions I hope are helping you students determine how to solve the questions in your JEE Mains exams. Right? Moving on to the next part. Among the given species, the resonance stabilized carbocations are. Among the following species, the resonance stabilized carbocations are. Right? So look at these given species once again. I've already told you how to determine the resonance stabilized carbocations, right? Here there is a double bond, so the double bond will move over here. A double bond, single bond, a positive charge will show resonance, right? They've asked you that only, right? So A will show resonance. Will B show resonance? Yes, there is a positive charge, double bond, single bond and a positive charge will show resonance. Will the C option show resonance? No. Because a double bond has two single bonds in between and then a positive charge will not show resonance. Look at the D option. In the D option, there is a double bond right next to the positive charge. Hence, once again, it will not show resonance, right? This structure cannot, this is a vinyl carbocation, cannot show resonance because a double bond is right next to the carbon on which there is a positive charge present. So they will not show. A and B will show resonance, right? Easy. So these kind of easy questions also come. You have to know about all of these things. Next question is, which of the following compounds possesses the most acidic hydrogens, right? Which of the following compounds possesses the most acidic? Once again, I told you, more the electron withdrawing groups attached, more acidic would be the hydrogen, more stability of the negative charge present, right? So what did I teach you? So whenever the hydrogen leaves, for example, the hydrogen will leave from here, the hydrogen will leave from here, and the hydrogen will leave from here, the hydrogen will leave from here. What will be left behind is a negative charge, a negative charge, a negative charge, and a negative charge over here, right? Now we have to look for the stability of the negative charge. More stable the negative charge, more acidic is the species. Now, can you see in the very first option, what option is that? That option is C triple bond N. Here also, once again, there is a CH and a negative charge over here and also a C triple bond N, right? So, this negative charge can show resonance over here. This can move over here, this can move over here, once again can move over here, can move over here. This can show resonance, right? But only two resonating structures can be shown over here. And look at the very fourth option once again. Here in the third option, once again, there can be just one resonating structure. In the second option, there is indeed a triple bond. I am guessing there is a triple bond present over here. So, there is just triple bonded sp hybridized carbon over there. There is no resonance. So, it is even much less stable. Now, look at this hydrogen over here. In the fourth option, the negative charge can actually resonate. Here is a double bond O. There is OMe. Here once again there is OMe. And here once again there is double bond OMe. Right? So once again, what you can see is that the negative charge over here can be stabilized over here, can be stabilized over here, and can be stabilized, bacha, over here, right? So this negative charge is actually three kinds of electron withdrawing groups attached. Hence, this hydrogen is indeed the most acidic. Even though you will argue that ma'am here OMe is present. Therefore, what it will do, it will interfere with the resonating structure. It will itself show resonance with this compound, right? You will argue with me for the same. I am agreeing with you. So, if I had similar structures and if I had to compare between similar structures where there was OMe present and the OMe was absent, I will definitely consider this criteria. But in this option, bacha, what is happening? In this option, can you see just 2 electron withdrawing groups are there? Here once again there is just 1 electron withdrawing group. Here there are 3 electron withdrawing groups. Hence, this hydrogen is much more acidic hydrogen and it will be taken away very, very easily because this negative charge is much more resonance stabilized. So, the fourth is the correct option, right? So, in organic chemistry, you have to actually consider a lot of variations, a lot of, what do you say, mix and matching to actually give the right answer, right? There is no such as definitive answers in organic chemistry because you have to consider a lot of factors. There are so many factors which are influencing just the acidity portion of it, right? Chaliye. Next is, which of the following has the shortest CCl bond? We have already covered this, I guess. We've already covered this, so we will be skipping this question. Next is, in the following compounds, the favorable sites for protonation are. Protonation, which means what? The addition of hydrogen. You are adding hydrogen, which will take up hydrogen very easily. Here, once again, you have to understand the language of the question. You see which takes up hydrogen very easily, which is a strong base, right? So, here you are actually identifying which of the following is a very strong base, right? So, always remember, here you are identifying a very strong base. Strong base is what? Strong base is which gives away electrons. Electron give away easily, right? Which gives away electrons easily, right? For example, look at this question over here. Now, bacha, here once again, I'm going to teach you another thing. Another thing, see, whenever such questions are given to you and you have to tell me, see, what is the first thing that I taught you? The first thing is always draw the lone pairs present on them. So, I'm drawing the lone pairs. Here once again a lone pair is there. Here once again a lone pair is there. A lone pair is there and a lone pair is there. So, I've drawn the lone pairs. The next thing is, ma'am, which lone pairs will be easily available and which lone pairs will be not. So, understand this thing. Whenever a lone pair is directly attached to a double bond, a lone pair is directly attached to the double bond, that lone pair, bacha, will always be ready to donate, right? Those lone pairs will always be available for donation. Available for donation, right? Because they are never participating in the resonance or in aromaticity, anything. So, these lone pairs which are directly bonded to a double bond or a triple bond will never participate in the resonance or aromaticity. So, they are available for donation, hence they are strong bases. So, look at these examples. Look at the A option over here. There is a NH2. NH2 group, ma'am, here will definitely show resonance because the NH2 group over here has what? The NH2 group is attached to the single bond. Hence, these electrons will participate in resonance. Hence, these are not available for donation, right? Not available for donation. Look at the B option. In B option, once again, these lone pairs are directly attached to a double bond. Can everyone see? Directly attached to a double bond. Hence, these are easily available for donation. So, B will easily donate. So, it will donate. It is a good base. It will donate is a good base, hence it will undergo protonation. So, whenever protonation is asked, which means what? Which can easily take up H+. Which compound will take up H+, which is the most basic compound, right? Look at the C option. Once again, the lone pairs are directly attached to a double bond, hence these are available for donation. These will also donate. Look at the E option. These lone pairs are attached to just single bonds, hence they are participating in resonance or aromaticity, whatever is present in them. Hence, these are not available for donation. Look at the D option once again. Directly attached to a double bond, hence available for donation. I checked nothing except this. I've checked nothing except this. I've just checked this, and this will never, I will never get any question wrong using this technique, right? So the favorable sites for protonation hence are B site, C site and D site. So the fourth option is correct, which has a B, C, D written in it. So the fourth option is correct. B will donate. Similarly, your C will donate. Similarly, your D will donate. Is this thing clear? Is this option, is this question clear to everyone? Right? Okay. Let's move forward. Let's move forward to the next question on the screen. The increasing order of pKb value for the following compound is. Now, what is a pKb value? Always remember that pKb is inversely proportional to basicity, right? More basic the compound, less will be the pKb value. It's exactly like pH, right? So pKb value, more pKb value, less will be the basicity. So just have to check the basicity of these compounds. So can you see here this nitrogen has a lone pair right next to a double bond. Hence, these lone pairs will be easily available for donation, while these lone pairs will be participating in aromaticity, hence will not be available. So here one lone pair is available for donation. Now look at the C option. C option once again. It is a NH option followed by a CH3 over here, followed by a CH3 over here and a NH option. These lone pair once again are easily donatable, and the CH3 group is actually causing the plus I effect, right? So the CH3 group over here, here is a CH3 group. It is actually causing a plus I effect, and here also a plus I effect. Plus I effect and plus I effect, right? So it is actually increasing the electron density. Now look at the option number B. In option number B, these electrons are, ma'am, participating in resonance, right? And here once again, these electrons are there. They are participating in resonance. These electrons are once again participating in resonance, right? But once again, can you see that these electrons might be participating in resonance with this nitrogen, but still your B compound has 3 nitrogens attached to it. Your A compound has just 2 nitrogens attached to it. Your C compound has just 1 nitrogen attached to it. Even though they are showing similar effects, but as the number of nitrogens are changing, hence what am I saying? Your B option will be the most basic compound. So the order of basicity will be, your B will be the most basic, followed by the A, followed by the C compound. So this would be the basicity order. But your pKb order will be what? They have asked you not the basicity but the pKb order. So the highest pKb will be of the C, followed by A, followed by B. So this is the pKb order. C will have the highest pKb value, right? Why have I done that? Then you will be like, ma'am, okay. In A option, these electrons are actually participating in resonance, hence the basicity should decrease. But can you also see that even the number of nitrogens are changing in all these 3 options? So whenever you have to compare between options, bacha, you have to scan these options very thoroughly, right? Even though these nitrogens are participating in resonance, but I told you the resonating electrons can be donated. If these electrons are participating in aromaticity, then I would say they are not participating in basicity at all. They are never donating the electrons at all. But the resonating electrons can still do what? Donate the electrons. How? Look at the resonating structure of first. I am looking at the resonating structure of first. The first has NH2, right? NH2, when it gives electron, it's become double bond, and this CH and this. So if this double bond comes over here, this double bond actually goes over here. So this NH actually gets 2 lone pairs and hence also gets a negative charge. So whatever electrons this nitrogen had, this nitrogen is receiving all those 2 electrons. So it is increasing the basicity overall, because these nitrogen's electrons can then participate in the basicity, isn't it? Now once again in the B option, something similar will happen. If these electrons are participating in resonance, it is actually giving its electrons to this nitrogen, hence increasing the basicity once again. hence increasing the basicity of this nitrogen. So because three nitrogens are in what? Vicinity of each other, are participating in resonance within each other, hence they are increasing the basicity of the compound. So the most basic compound is B because it has three nitrogens, followed by A, it has two nitrogens, followed by C because it has just one nitrogen, right? So that's why I'm telling you that organic is not just a clear-cut road, just like your maths. It's not a black and white road, it's a grey road that you have to take. It has all the seasons in it, right? So you just don't have winters or summers, you have all the seasons in it. Just like all the seasons keep changing, so does its rules. You have to mold your thinking. You have to keep a very, very open and broad mind while solving these questions. If you don't have a very open and strong broad mind, you will be like, okay ma'am, these electrons are participating in resonance, hence it's what? It decreased its basicity. But look at what it is participating in. It is actually giving electrons to this nitrogen, hence increasing the basicity. Once again, here these are actually giving the electrons to this nitrogen, increasing the basicity. Here these are actually giving electrons to this nitrogen, hence also increasing the basicity, right? Understanding this thing, right? So B is the highest basic, followed by A, followed by C. So go through this question once again. Just, you know, when you actually see, I've already explained to you how to actually do this question. Now what you have to do once you get the PDF of this file, go through all the questions one by one and just think, like, why did ma'am say that this is the correct answer, right? You have to think upon it. Then your brain will automatically figure out, automatically join all the dots that I have told you in this entire lecture, right? Now look at the B compound. I think many students are facing problem in the B. For example, this compound looks like this. This is nitrogen over here. This is nitrogen over here. Here is a double bond, something like this, followed by here is NH2, here is something like this compound, right? Now here, bacha, what is happening? It has a lone pair. It has a lone pair over here, and this one also has a lone pair over here. Now, bacha, if this lone pair participates in resonance, what is happening? Look at the very first resonating structure. Very first resonating structure is this. Here is the nitrogen. Here the double bond comes, and here the single bond comes. One lone pair comes over here, another comes over here. It gets a negative charge, and something like this happens over here. NH2, here it gets a positive charge. Here. Right? So something like this will happen. Chaliye, let's move on to the next thing. So can you see here what I meant to explain is, here the nitrogen is getting more number of electrons which it can then participate for the basicity. Once again, this nitrogen can also donate, hence its basicity is even increasing even more due to resonance. As we know that inductive effect has a lesser dominating effect than resonance. So due to resonance, more electron density will increase as compared to the inductive effect, which is followed in the C option, right? Okay. Next is hyperconjugation is a permanent effect. Is this a true statement? Absolutely true. Always remember your inductive effect, your resonance and your hyperconjugation all are permanent effects. Only your electromeric effect is a temporary effect. Hyperconjugation in ethyl cation, this is a ethyl cation, okay, involves the overlapping of CsP2 H1s bond with the empty 2p orbital of the carbon. So whenever they are talking about hyperconjugation, so hyperconjugation looks like this: CH3, 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 and here it would be the CH2 plus over here, right? So here, bacha, what will happen? This hydrogen will actually leave and will participate in what do you say? All of these hydrogens actually participate in your hyperconjugation, right? So the carbon to which the hydrogen is attached is actually a sp3 carbon. So the bond that is participating in resonance is the sp3 and of hydrogen's 1s orbital of hydrogen, and the sp3 orbital of carbon is actually participating in resonance. So here the carbon is not sp2 hybridized but sp3 hybridized. Hence this option is actually incorrect. It is a false option. So the sp3 carbon, the hydrogen of the sp3 carbon is actually participating in hyperconjugation, and then this hydrogen's 1s electron actually enters the vacant 2p orbital of the carbocation. The carbocation has a vacant 2p orbital, right? This is the structure of carbocation. This is structure of carbocation, has a vacant 2p orbital where the hydrogen gives away one of its electrons, right? So this is what actually happens, right? So this is a false statement because CsP3 and H1s bond actually participate in the hyperconjugations, right? Next is the correct stability order of carbocations is. You have to tell me which is the correct stability order of the carbocations is. Right? Always remember, whenever you are telling the stability of either alkenes, remember, of either alkenes, of either your carbocations or of either your free radicals, you have to use, like I know that resonance has the most dominating effect. See, if resonance is happening, you have to use the, like resonance is the most dominating effect. So the resonance stabilized alkene or the resonance stabilized carbocation or the resonance stabilized free radical will be the most stable. But in the questions where resonance is not happening, there you have to check for hyperconjugation. Very, very important. For just these three species, not any other species. For alkenes, for carbocations, for free radicals, you have to check what? For alkenes, for free radicals, for carbocations, you have to check hyperconjugation happening. Wherever the hyperconjugating structures are more, that species is actually what? That species is actually your most stable species. So look at here they have asked you about the stability of the carbocations, right? So here can you see this carbocation has 9 alpha hydrogens. For example, this carbocation has just 3 alpha hydrogens, right? And okay, how do you check the stability if students are asking me that? Then bacha remember, for example, there is a carbocation over here. Now this carbocation is actually sp2 hybridized. Right next to the sp2 hybridized carbon, there should be a sp3 hybridized carbon. This is the condition for hyperconjugation, to which at least one hydrogen should be attached. So how many hydrogens are attached to this alpha carbon, which is actually sp3 hybridized, will dictate the stability of the carbocation, of the alkene or of the free radical, right? So this simple funda is actually asked. Okay, right next to the carbocation, right next to the alkene, right next to the free radical, there should be sp3 carbon to which hydrogen are attached. More the number of hydrogens, more the number of alpha hydrogens, more will be the hyperconjugating structure, more stable will be the compound. So here this is the carbocation. Right next to this there is a carbon which is sp3 hybridized. It has 3 alpha hydrogen. Now bacha, this is the carbocation. Right next to this there are 3 2s are 6 alpha hydrogens, and right next to this is a simple methyl carbocation. Hence this is the most unstable because it has no alpha hydrogens here. So the most stable will be the one with 9 alpha hydrogens. So I'm seeing that the third option is the correct. It has 9 alpha hydrogens followed by 6 alpha hydrogens, followed by 3 alpha hydrogens, and followed by 0 alpha hydrogens, right? So this is a stability order. More the number of alpha hydrogens, more stable will be the compound, whether it is an alkene, whether it is a carbocation, or whether it is a free radical, right? Okay, let's move forward. Which of the following is the correct hydride affinity order of carbocations? Which of the following is the correct hydride affinity of the following carbocations, right? Hydride affinity means what? Which will readily take up the hydride ion, which is the H minus ion. Hydride affinity. See, if I'm very stable carbocation, why will I easily take up anything? I'm already very stable. So you have to check, if I'm very stable, I will not take up any other species because I'm already very stable. So we have to check the stability of the carbocation. Wherever the carbocation is least stable, they will have the highest affinity for the hydride ion, right? So I'm writing it over here. Carbocation which is the least stable, which is the least stable, Carbocation, which is the least stable, has the, right? So carbocation which has the least stable has the highest hydride affinity. Affinity to it, right? For example, look at the questions over here. Which of the following is the correct hydride affinity over? Look at this carbocation. This carbocation has, this is the sp3 carbon attached and it has 0 alpha hydrogens on it, right? So this is the least stable and this is also a primary carbocation. Can everyone see? This carbon is primary and to this primary carbocation there are no alpha hydrogens and there is no resonance. I'm writing no resonance, no resonance stabilized carbocation, no alpha hydrogen, and also it is a primary carbocation. Hence this carbocation is already very unstable, therefore it will take up the hydride ion very easily. So this becomes a very good contender. So A becomes the right option. Let us also check the other options. Here the carbocation is attached to 6 benzene rings. Can you see? I'm writing the B option over here. It has 1 benzene ring over here, right? So let us draw it correctly. Benzene ring is like this. This is the benzene ring and here once again here is a carbon and here is a benzene ring and here once again is a benzene ring and here's a carbocation. So this carbocation can be resonance stabilized from here, resonance stabilized from here, resonance stabilized from here. So this carbocation is actually resonance stabilized, right? So I'm just writing resonance. This is perfectly stable. This will not attract the H minus ion itself to it because I'm very stable. Why will I attach anything to myself? I'm already very stable. So this will not attach any hydride ion. Look at this. This cyclopropyl propyl cation, bacha, it is very, very stable. It is very stable. Always remember this thing. So whenever I'm asking you the order, this cyclopropyl, this is tricyclopropyl cation, it is very stable. It is even stable than the benzyl carbocation. Exactly. So this is even stable than your B counterpart, right? And after that, because they have asked you the order of carbocation stability, so I'm just going to write you. And let us also check the D option. The D option has 1, 2, 3, which means it has 9 alpha hydrogens attached over here. Now, because it has 9 alpha hydrogens attached here, so can you see that this carbocation is once again stable through hyperconjugation, right? Hyperconjugation. So I'm writing here the stability of all carbocations. So here I'm writing the stability of carbocations, right? I'm writing the stability of carbocations. The most stable carbocation is the C carbocation, followed by your B carbocation. Okay, remember this is even stable than your this benzylic carbocation, tribenzylic. So always remember this has this kind of carbocations have unusual stability, right? This has been found through research and it is a very good, what do you say, it is this, these kind of questions have become what do you say, like these are very common in your JEE exam now. These are very kind of favorite questions as in your JEE exam. So remember these kind of carbocations, whenever like these cyclopropyl rings are attached to a carbocation, they become even more stable than a benzyl carbocation. So this carbocation is much more stable, followed by B, and then followed by your B because it has resonance in it, followed by D because it just has hyperconjugation in it, followed by your A. So this is the stability of carbocations. But it has asked you the stability of hydride ion species. So the correct answer would be that the hydride ion will be attached easily on A, followed by D, followed by B, followed by C. So this is the correct answer that you will give. This is the stability of carbocations. More stable the carbocation, less will be the hydride affinity. So the hydride will be affinity, means what? Hydride loving, right? So the hydride will be attacked on A the most, followed by D, followed by B, followed by C. C is very, very stable, unusual stability. So many teachers will give you examples of in this compound dancing resonance is shown. But if you check the research papers, there is nothing like dancing resonance ever mentioned in any research paper. So that is just a made up term made in quota classes. Do not go with those terms once again, right? So this is how you actually approach these questions, right? So always remember that this carbocation is very, 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 very stable, right? Very, very stable. Moving forward to the next question. JEE Mains 2022 question, and arrange the following carbocations in decreasing order of stability. Once again, we are checking the stability of carbocations. As I told you, either resonance should be, okay, whenever we are checking the stability, always remember, whenever we are checking the stability, always remember that aromatic compounds are the most stable compounds, followed by the resonance stabilized compounds. Whenever there is resonance shown, they are more stable, followed by the hyperconjugation compounds, right? Followed by your electromeric effect compounds, wherever there is a electromeric effect shown, followed by your inductive effect, So inductive effect has the least effect out of all of these GOC effects that you study in GOC, right? So remember one thing, inductive effect has the least effect on any stability. Understanding this thing? So look at the A option, which is a carbocation, right? So look at this carbocation over here. This carbocation actually is showing a plus I effect, right? Along with the plus I effect, but can you also see another thing, that here this carbocation has 2 hydrogens here and 2 hydrogens over here. So it has 4 alpha hydrogens, which means this carbocation is stable through hyperconjugative effect. Look at this carbocation. Up, can you see this carbocation, ma'am, is right next to the oxygen which has lone pair of electrons. What did I teach you? This is a very popular compound asked in so many questions, in so many variety of questions, but the logic behind it remains the same. That whenever a carbocation is right next to a compound which has a lone pair of electrons, remember this thing, whenever a carbocation is right next to the lone pair of electrons of atom, that carbocation is very stable, extremely stable, right? Due to resonance, obviously, due to resonance, this is extremely stable. Similarly, your C part, look at the C part. In C part, you will argue, ma'am, once again, it has 1, 2, and once again, 4 hyperconjugating hydrogens. 4 alpha hydrogens are present. You will argue with this, 4 alpha hydrogens. This one also has 4 alpha hydrogens. Then, ma'am, how will I compare the stability or the stability effect? Now, bacha, because they have the same alpha hydrogens, I have to resort to another method. The another method is that this carbocation is attached to an oxygen, and this oxygen from so far away will, because this oxygen is more electronegative, hence this oxygen will actually have a minus I effect on this carbocation. It will have a minus I effect, because whenever an electronegative atom is attached, it shows a minus I, which is a electron withdrawing effect, right? So minus I is electron withdrawing group to this carbocation. If I'm already positive, you're taking away more electrons from me, you're making me more positive, more unstable, right? If I'm positive, I need plus I effect, which means this CH3 groups will also show what? Plus I effect, right? So can you see? Your A is much more stable than you see. The most stable carbocation hence is the B carbocation, followed by your A carbocation, followed by your C carbocation. Is this thing clear? C carbocation is even less stable. Why? Because it's oxygen, because it is more electronegative. Always remember one thing. Whenever anything more electronegative is attached to any group, whether it is oxygen, whether it is nitrogen, chlorine, anything, if it is more electronegative than carbon, it will show minus I effect. Minus I is electron withdrawing effect. If I'm positive, you are taking away electrons from me, you're making me more and more what? You're turning me into much more of unstable compound, right? So this is a stability order. That's the only thing they have asked, right? Arrange the following carbocations in order of stability. So this is the final stability order. This is the final stability order, right? Next, Among the following, the aromatic compounds are. Now we have entered another territory of aromatic compounds. You have to answer. Among the following, the aromatic compounds are, right? What is the criteria of aromaticity? I am writing it down here. Aromatic compounds, very first thing should be cyclic. The second thing is every atom in that cycle, every atom must be conjugated, or conjugated means what? Must be sp2 hybridized. Every atom in that cycle must be conjugated, means what? Must be sp2 hybridized. Next is it must be flat in nature, right? It should not be a 3D molecule. Last is it should follow the Huckel rule, which is 4n plus 2 pi electrons rule, right? It should follow the Huckel rule, right? So look at this compound over here. This compound already has a sp3 carbon in the cycle, hence it can never be aromatic, because in aromatic all the atoms must be what? Conjugated, which means sp2 hybridized. Look at this B, it is a benzene, classic example of aromatic compounds. It is definitely aromatic. So this is aromatic. Look at this compound, C compound, it has a negative charge over here. This negative charge will definitely participate in resonance. Why? This negative charge will go over here, this double bond can go over here, then this double bond can go over here. Can everyone see that this negative charge is participating in resonance? And also when it participates in resonance, it becomes 1, 2, 3, 4, 5 and 6 pi electron system. Can everyone see? After these electrons participate in resonance, it becomes a 6 pi electron system, which is definitely a aromatic system. It is following the 4n plus 2 pi electron rule. So C is also aromatic. Now look at the D compound. Here once again, this has a positive charge. Now this is cyclic. This is cyclic. All the atoms are conjugated, which means all the atoms are sp2 hybridized. This is double bond sp2, 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 sp2. A carbocation's hybridization is also sp2. This is a carbocation. Hence, this is also sp2 hybridized. Yes. Is this a planar or a flat compound? Yes, this is a flat compound or a planar compound. Flat or a planar in just one plane, right? The last is it following the 4n plus 2 pi electron rule? No, it actually has 1, 2, 3 and 4. It actually has 4 pi electrons. So remember one thing, whenever any element follows the first three rules, which is they are cyclic, they are conjugate, they are flat, but follows the 4n pi electron rule, then they are actually anti-aromatic. What are they? They are actually anti-aromatic compounds. Very, very important. The first three conditions remains the same. They are cyclic. All of them are conjugated, which means all of them are sp2 hybridized. The third is, it is a flat molecule. These conditions satisfied. But it is a 4 pi electron system. 4 pi electron system, whenever the number of electrons, remember it in a way, that whenever the number of electrons are equal to the number which you will find in the table of 4, like 4 2s are 8, 4 3s are 12 electrons, and then 18 electrons, 16 electrons, sorry. Okay, if you find electrons in such a way which are present in the table of 4, those compounds are anti-aromatic compounds. Anti-aromatic compounds, which are the least stable compounds, least stable. They are so less stable that they don't even exist. They're not at all stable at all. If they're not stable, they will not be formed. They will not even exist. So they are least stable. 4 and pi compounds are least stable, right? So only two aromatic compounds are there, which is benzene and this C compound. Understood? Next question. Which of the following is the strongest acid? Very good question once again. Strongest acid means what? Once again, which easily gives away H+. The A option is a normal cycloalkane, will not give away H+. It is not an acid. It is a non-polar compound, I know. Move on to the B option. Here, if I take away, I cannot take away hydrogen anywhere from the benzene ring. It is not even possible, right? They do not donate hydrogen. They do not become carbocations, right? If it gives away H+, what will be left behind is an anion. Those anions are never ever stable, so they will not be formed. And if I take away H plus from here, then what will happen? A negative charge will be left here. This negative charge can then participate in resonance. Yes, it can happen. This negative charge can then participate in resonance, and then it can be a better acid, right? But look at the other compounds. Other compounds, if I take away hydrogen from here, H plus, if I take away H plus, what is left behind is a negative charge. Now this negative charge, look at this compound. This is a cyclic compound. This, all of the atoms are sp2 hybridized. This is a conjugated system. This is a planar system, but it has how many electrons? 1, 2, and this lone pair has 3, 4. This has 4 pi electron system, which means this is anti-aromatic. What kind of system is this? This is an anti-aromatic system, right? Whenever a system is anti-aromatic, it means what? It means it is unstable. So if I am giving away my H plus, I am becoming unstable. I will not even exist. Why will I give away H plus? This is not even acidic at all. It will never give away H plus, because after giving away H plus, I am becoming anti-aromatic, unstable. So this will not give away H plus. D option, again, if I take away H plus from here, so here will be a negative charge. Now this negative charge will once again do what? Resonance inside this ring. After doing resonance, this is becoming a 1, 2, 3, 4, 5, 6. 6 pi electron system, which is a aromatic compound. So whenever the aromatic compound is found, it is very stable. So look, as soon as I give away my H plus, I am becoming an aromatic compound. So I will be more acidic. Take away my H plus, because after that I am becoming so much more stable. So this will be the most acidic compound. So can you see how aromaticity is being used in actually identifying which one will be the most acidic compound, right? So all of these factors are really essential. So if you hadn't practiced questions, if you just know what aromatic compounds are, you won't be able to actually do even one question of GOC in your JEE Mains exam. That's why emphasis on PYQs is given so much. Understanding this thing? So this is how anti-aromatic compounds and aromatic compounds are formed, right? Understood? Now, ma'am, because after losing my H plus, I'm becoming aromatic, so I will be the most acidic. So the most acidic compound will be the D compound, right? D compound, this is what they've asked, right? In B, definitely resonance is present. Definitely the negative charge is stabilized by resonance. But still, resonance has a weaker, resonance stabilized are still weaker stabilized compounds as compared to the aromatic. Aromatic are the more stable. There is a hierarchy of stability in your organic chemistry. The most stable are your these kind of compounds, which are aromatic, followed by resonance, followed by hyperconjugation, as I just told you the series over here. I just told you here, right? Aromatic compounds are the most stable, followed by the resonance hybridized compounds, right? Perfect. Next question on your screen. Which will have the highest enol content? JEE Main 2022 2022 question. Which one will have the highest enol content? Very good question once again. Extremely great question once again. So look at this. What is a enol compound content? So remember one thing. There is a kind of tautomerism which is called the keto-enol tautomerism. This is a keto group, right? So right next to the keto group, there is a carbon which is known as the alpha carbon. This alpha carbon must have one hydrogen. This is a keto compound. Keto group, right? C double bond O. So this CH group over here actually happens what to this CH group? This oxygen has a lone pair of electron. So this oxygen can actually take away this CH. Why? Because as I told you, this CO group is an electron withdrawing group. Hence this hydrogen becomes acidic right next to it. So this hydrogen is acidic, hence this oxygen takes up this hydrogen. Now, bacha, what happens? It shows a tautomerism like this. It shows a tautomerism like this. And what will happen? It will form, this is carbon over here. The O will have the H. So, therefore, this bond, double bond will move over here. This will get a double bond character. And this kind of compound will be formed. This kind of compound. So, can you see here what has happened? This is called the keto isomer and this is called the enol isomer. What is enol isomer? where the double bond and the OH group are on the same carbon. Can everyone see that? That the OH group and the double bond are on the same carbon. Here is the OH group, are on the same carbon. It is called the enol form. Generally, in 95% or 90% of the cases, what happens? Your keto forms are more stable because enol, whenever a double bond and the OH are on the same carbon, it is not a stable species. They are not stable at all, right? They are not stable. So, in generally 90% of the cases, your keto form is more stable than your enol form. But there are certain cases where enol form actually becomes more stable. And when does that happen? It happens when, bacha, your enol form actually becomes more stable. When it happens, for example, after becoming the enol form, I'm actually becoming aromatic. For example, your benzene ring. And after becoming the enol form, can you see the phenol form is actually a enol form because the same carbon has a double bond and a OH group, right? But this is becoming aromatic in nature. So whenever a enol form converts into aromatic in nature or any other thing, there is a hydrogen bonding forming, there is formation of H bonds, so your enol form will be more stable. So due to few of these reasons, few of the circumstances, your enol content actually increases. Most of the cases, keto content is more stable. I hope this thing is clear. Now look at these. These are all the keto isomers drawn over here. But they have asked you about the highest enol content. So I have to just create their enol forms out of their keto forms. Now if I create the enol form from here, A, can you see that this C double bond O group has a alpha hydrogen here, this has a alpha hydrogen here. So the lone pairs on this oxygen will abstract this hydrogen, therefore this double bond will move over here, this will abstract this hydrogen, hence this double bond will move over here, right? So what kind of isomer will be formed? I'm drawing the A isomer over here, A enol form. Once again, there is a cyclohexane molecule. And here it would be the OH group, here once again the OH group, right? And here it would be a double bond and here it would be once again a double bond. So these kind of double bonds would be formed, right? So this is the first isomer. Here once again I can make it can show H bonding here. It can show H bonding here, right? This OH and that H can show H bonding. Next, B isomer. B once again here, if I talk about here, this can be the alpha hydrogen for it. So these hydrogens will abstract this hydrogen, this double bond will come here. Once again, look at this oxygen. This oxygen has this alpha hydrogen, it will abstract this and then this double bond will move over here, right? Now for the B option, what will happen? It will actually form something like this OH and here it will be the double bond and here it will again be the OH and here it will be a double bond, right? So these kind of products are formed. Now once again here there is no H bonding, hence it is even less stable. Now look at the C compound. In C compound, bacha, what is happening? In C compound, bacha, what is happening? In C compound, this can be, if this is the oxygen, this is the alpha hydrogen for it. So it will abstract this hydrogen, the double bond comes over here. If this is the oxygen, this can be the alpha hydrogen for it. So it abstracts this hydrogen and the double bond comes over here. Once again, if this is the oxygen, this can be the alpha hydrogen, this abstracts the hydrogen and the double bond comes over here. So what will eventually happen? A structure like this, a OH group will be here, OH group will be here, OH group will be here, will be formed, right? Now when I'm forming this, a double bond, first double bond comes over here, second one here, third one here. So can you see a benzene ring is formed, an aromatic compound is formed as soon as it is converted into the enol form, right? So the enol form hence is very, very stable over here because the enol form, look at this enol form, right? This enol form is very, very stable. Hence it will, because it is becoming aromatic, this will show the highest enol content. Because the enol content is more stable. It is aromatic. Hence, instead of the keto form, its enol form will be more stable. Hence, it will have the highest enol content. Is this thing clear? So, the highest enol content will be shown in the C isomer followed by B, because B once again has, sorry, A, which once again has a little potential of hydrogen bonding in them. Okay. So, this enol form will have, this C option will have the highest content of enol form, because after forming the enol isomer, I am actually becoming more and more what? I am becoming more aromatic, more stable. Next question. Next question is, which of the following compounds, the one which shows the highest dipole moment is? Again, a very interesting question. Among the following compounds, the one which shows the highest dipole moment. Dipole moment is what? Whenever two poles are created. The two poles are created whenever it remains in such a two-polar, bipolar condition, a positive and a negative, that will show the highest dipole moment. Now, look at all the examples given over here. They have not given you anything with regard to your, what do you say? Most of the dipole moment questions you actually get from a chemical bonding chapter, right? Then you compare ki where the electrons are moving and what not. But this is an organic chemistry question, okay? Look at this question. Now, bacha, here, always remember, whenever a double bond or a multiple bond is outside the cycloalkane ring, then that double bond is actually called a exo bond. What it is called? Exo bond. And that exo bond can be broken in such a format that, for example, here it is related, attached to oxygen. Oxygen is more electronegative. So, therefore, this bond can be broken down in such a manner that the oxygen gets a negative charge and hence this carbon gets a positive charge. So, this kind of dipole can be created out of here because the oxygen is very highly electronegative. So, it will attract electron towards itself. Then, two poles can be created over here. But I am also seeing the D compound, right? I am scanning the options and I come across the D option. Look at the D option. In the D option, what you will observe? In the D option, bacha, what you will observe, okay, look at the D option, is very, very crucial. Here, bacha, can you see the cyclopropane ring, right? Here, there is once again an exo bond. Now, I can break this exo bond in any way. Because here there is also a carbon, here also there is a carbon. There is no electronegativity difference. So, I can break this bond in any manner that I want. So, here, bacha, I will break this bond in such a manner that this will get a negative charge and this instead gets a positive charge. Whenever I break it in such a manner, can you see? Look at the cyclopropane ring. This ring actually becomes once again an aromatic ring. Why? Because this gets a 2 pi electron system, doesn't it? This becomes a 2 pi electron system ring. This is a this compound is a cyclic compound. First option of aromaticity. Second is this compound this compound is conjugated. All the atoms are sp2 hybridized. Third is this is a planar compound. Fourth is this is following the Huckel rule, which is the 4n plus 2 pi electron rule, which means this is a aromatic compound. Now look at this ring over here. When I give it the entire electrons, right? Let me draw it much better way. If I break this bond in such a manner that this ring gets a negative charge while this one gets a positive charge. So this ring is actually becoming a 2 pi electron ring. Now look at this ring over here. This ring over here has a 1, 2, 3, 4, 5, 6. How many electrons are there? There are 6 pi electrons present here. Can everyone see? 6 pi electrons. Once again, this has also gotten converted into aromatic ring. As soon as I broke the exo bond, both of the ring got aromaticity in them, right? So, one of the ring got a positive charge, the other one got a negative charge. So, as soon as I am getting converted into a dipole, I am actually becoming aromatic. So, why will I not show the highest dipole moment? As soon as you are creating charges on me, I am becoming more stable, I am becoming more aromatic. Hence, this will definitely, D option, will show highest dipole moment, because after converting into two dipoles, two charges, two separate charges, I am becoming aromatic, more stable. Both the rings are becoming aromatic. Hence, bacha, D will show the highest dipole moment. So, look at over here. How we have used aromaticity in determining your first of all enol content, your acidity, right? Your enol content, your acidity, your basicity, and even your dipole moment. So once again, emphasizing on how much important are to do those questions, are to do just the PYQs, because they contain such a vast knowledge, right? These PYQs are designed such beautifully. They're really, really nice questions. Okay, let's move forward to the next question. Once again, JEE Main 2023 question. This is a direct rip-off of a JEE Advanced question. As I keep repeating, if you are a very, very good student and if you've already done all the PYQs, know all the PYQs by heart, know all the reasoning of the PYQs, I'm talking about especially chemistry, especially organic chemistry, then please do not refrain from doing the PYQs of your JEE Advanced exam, especially 2 years back, 3 years ago, 4 years ago. PYQs are very, very essential because same questions are repeated in your JEE Mains exam. This is one such example. As in your JEE Advanced, now in your JEE Mains asked last year. Look at the question. Correct statements for the given reaction are. So a kind of reactions are given over here, right? So the correct statement for this, what would be the correct statement? The compound A, compound B is aromatic. So let us just do the reaction first of all. What they have done, they have given you a compound A and they are trying to react it with 2 equivalents of OH minus. What is OH minus? I've already discussed it with you plethora of times. OH minus is a base. What is the function of base? To abstract H plus. So OH is here, it will abstract the H plus from here, it will abstract the H plus from here, right? Because it is a base, you are using 2 equivalents, so it will abstract 2 equivalents of OH from here. Now the B compound that will be formed will look something like this. Here is the double bond O, here is the double bond O, and here it is the O minus over here. Here once again the O minus is present over here, right? So this is the B compound form, right? And next is, let me just draw it in a better way. Like this, like this, like this. Here is the double bond. Here is the O minus. Here is the O minus. Here is the double bond O. Here is the double bond O. The first question is, compound B is aromatic. Is the compound B aromatic? How will I see if it is aromatic or not? I would have to convert it into a aromatic compound. So can you see, these are once again exo bonds. So exo bonds can be broken. It is attached to more electronegative oxygen. So the oxygen will get a negative charge. So when I convert the exo bonds into simple plain single bonds, what will I get? What kind of compound will I get? I will get a O minus over here and a double bond, again a O minus over here, and then again O minus over here. If the negative charge goes over there, this carbon will actually get a positive charge. Once again a O minus over here, this carbon will again get a positive charge, right? Now bacha, is this compound aromatic? Is that what they have asked, right? Now compound B is aromatic. Look at the compound B. Look at the compound B. This is the compound B, right? I can write the compound B either in this manner or in this manner. They're all the same thing. I've just converted this bond into a single bond, right? Why? Because oxygen is more electronegative, so it will pull the electrons towards itself. It can get a negative charge. Now, can you see this is cyclic? Yes. Are all the atoms sp2 hybridized in the cycle? This carbon is sp2 double bond. This is sp2. These both are carbocations sp2. Yes, all are sp2, all are conjugated. Is this planar? Yes. Last is this following Huckel's rule? How many electron system is this? This is just 2 pi electron system, right? Just 2 pi electrons are present. Definitely aromatic, 2 pi electron, compound B is aromatic. A statement is correct. The next is the completion of above reaction is very slow. Is the completion of above reaction very, very slow? No. Why would it be slow? It is converting into an aromatic compound. The product is aromatic. So when the product is very stable, the reaction will be fast. So this is a false statement, right? This is not true. This is not a true statement. Next is A shows tautomerism. This is the A compound and it is asking if it is showing tautomerism. Let us see. I'm drawing the A compound once again over here. This is the A compound. Here is a double bond. Here is the OH. here is the OH, here is a double bond O, and here is a double bond O, right? Tautomerism, I just taught you what is tautomerism. Now look at this keto group over here. Right next to this keto group, can you see any hydrogen, alpha hydrogen over here? Look at this carbon already has 1, 2, 3, 4 bonds. It has 0 alpha hydrogens. Look at this carbon over here, it has 1, 2, 3, 4 bonds, 0 alpha hydrogens. So these ketones cannot show any enol forms. But check the enol form. Isn't this an enol form? To the same carbon, there is a double bond and a OH group. So this is an enol form. So can I convert this enol form into a keto form? Yes, definitely. How will I do that? I will just do the opposite of what I did when I convert keto to enol form. What will I do? I will just give this hydrogen, right? I will just give, so I'll just remove all these pink lines so that it is much clearer, right? Now, bacha, what will I do? This is the hydrogen, right? So I will give this hydrogen back to the carbon next to it. I'm giving this over here. And I will move this double bond to this carbon, right? So I can convert it into a keto form like this. It can get converted like this, this, this. Here is a double bond O, here is a double bond O. So what I do, I gave this double bond over here. Here's a keto form. And this hydrogen actually comes over here, and here is the OH group, right? So yes, I can convert this A compound into tautomeric compound, which is the enol form, right? So this is definitely showing tautomerism. I just made you the tautomeric product. So this is showing tautomerism. The bond lengths of CC in compound B are found to be same. Like all the CC bonds in the compound B are same. This is definitely true. Why? Because the B compound is aromatic. In aromatic compounds, all the carbons are in resonance with each other. Hence, all the bonds are equivalent in length, which means every bond has an equal double bond character in it. Because it is an aromatic compound, all the carbons are in resonance with each other. Hence, they will have what? Hence, they will have same bond lengths, they will have same bond energies, everything. Easy? To question, great question actually. I direct rip off once again from your JEE Advanced, right? So JEE Advanced questions are so many times repeated, especially there were chapters from metallurgy, right? Metallurgy questions were directly repeated from JEE Advanced. So whenever I used to teach metallurgy, which is no longer in a syllabus, but it is in your JEE Advanced syllabus, so many questions were a direct rip off from a JEE Advanced syllabus, right? But right now what I can advise you is from your JEE Advanced question, if you still have time, definitely do all the organic questions which have been asked. Definitely do. And the other thing which you should definitely do is do the questions from inorganic chemistry, right? Physical chemistry, no. Physical chemistry is really difficult in a JEE Advanced. Never such difficult physical chemistry have been asked in the entire history of your JEE Mains exam. But yes, inorganic and organic chemistry must be done from your JEE Advanced previous year papers. Just a reminder to anyone who has time on his hand. So please refer to this as well. But also, once again, telling you guys to not spend too much time on solving just the JEE Advanced question. Please pay attention to your strengths more. Whatever you are strong at this point, work hard on making it much more stronger, because this 1 month is enough to make you forget things, to make you think that you already know some stuff. But if you are not practicing it enough at this point of time, please mark my words that you have forgotten at least 50% of it, right? Because these 30 days are really crucial. Not even 30 days, the last 20 days, 22 days, whatever are remaining, right? 25 days. So these days are very important for actually making your stronger topics even much more stronger. Whatever is weak or whatever is remaining behind, especially in chemistry, just do the PYQs, just understand the PYQs. That's why this series is there. If your organic is very weak or your organic is very strong, for both of the cases, this series serve the purpose well, because you're doing the PYQs, you're understanding the mechanism, you're understanding everything, right? So once again, focus on the stronger topics much more. Do not focus on theory so much. So for the physical chemistry, once again, you should definitely have a formula sheet and just try to solve as many questions as you can. For inorganic chemistry, you must have notes where everything is written down in the condensed form, and then solve as many questions as asked in your inorganic. Inorganic chemistry, you must definitely do the PYQs, because once again, application part is asked. And if you're not familiar with the application part, then you might just lose marks on 2 to 3 questions from inorganic chemistry, and those 2 to 3 marks are really very simple if you just understood the concepts, if you just understood the applications asked in your exam. The last, in organic chemistry, please, your theory part should be strong. Your what is SN1, when will be the SN2 reactions conducted, in what solvent it would be conducted, when would elimination happen, what are the reagents, and for example, what does KMnO4 do? KMnO4 does a lot of things, right? It oxidizes even alkanes. What kind of alkanes it oxidizes? It oxidizes alkanes, alkenes, alkynes, your aldehydes, your ketones, your acid derivatives, right? Not ketones, obviously, not ketones, your acid derivatives. So all of these things, you must have it in handy. You must have a reagent list for you to take with you before your exams commence, right? So once again, informing you, and as much as the time permits, I am planning a series for you to help you in your journey, especially for your reagents, especially for your organic chemistry, especially for your inorganic chemistry. So we're definitely coming with that up. But yes, PYQs should not be missed. So we are definitely focusing on PYQs as well as the other things that we just talked about. Okay, now let us move forward to the next question, which is this. Arrange the following compounds in decreasing order of basicity. You have to arrange these compounds in decreasing order of basicity. We've already done a lot of questions based on that. What is basicity? Once again, basicity is the ability to donate electrons, right? What is basicity? Ability to donate electrons, right? Ability to donate electrons is basicity. Now look at this question. Can you answer this? Can you answer this? We've already discussed so many questions related to this. So look at over here, look at the first question. Whenever I told you, whenever you see such options, the very first thing you have to do is just make the lone pairs on every atom that you come across. So can you see the oxygen also has a lone pair? The nitrogen has lone pair, the nitrogen has lone pairs, right? Here also the nitrogen has lone pairs, here also the nitrogen has lone pairs. So I've drawn the lone pairs. Now in the first option, ma'am, which will donate better, the oxygen or nitrogen? Remember this thing. Whenever I'm more electronegative, means what? I'm keeping the electrons to myself, I'm not giving it away. More electronegative the species, it will hold electron to it more closely and will not give away electrons. So when I'm comparing between oxygen and nitrogen, right? So if I'm comparing the electronegativity, oxygen has higher electronegativity than nitrogen. Therefore, oxygen will not donate. So oxygen will not donate electrons as easily as nitrogen will donate, because oxygen is more electronegative. Understood? Next option, look at this electrons over here. These will also donate. Why? Because these electrons are attached to a double bond. So whenever a double bond is there, they will not participate in resonance. They are definitely available to donate. They can donate. This can also donate. Look at these electrons. These electrons are participating in resonance, hence will not donate or will donate less. Look at these electrons. These electrons are once again participating in resonance. Hence, also after participating in resonance, it is becoming a 6 pi electron system, right? 1, 2, 3. Just count the pi bonds. 1, 2, 3, 4, 5, 6. Pi electrons are 6 pi, which means it is aromatic. So, these lone pairs are participating in aromaticity, never available for donation. So, these are not available for donation, hence the least basic. So, you have to arrange in the order of basicity. So, the most basic compound. So, can you see? This nitrogen is attached to an oxygen, which is actually a electron withdrawing group due to its minus I effect, right? So, it is actually taking away electrons to itself because it is much more electronegative. So, the donation capacity of this will reduce due to the minus I effect of oxygen, right? We've discussed a similar question even before as well. So, see that the type is similar. every year the type of questions asked remain, they follow a pattern, they remain similar. You just have to understand what is happening. If you understand very thoroughly the entire mechanism, why was that the order, and you just didn't mug up it, then you are very good to go. If you just are mugging up the orders, that is very, very bad for you. It is equally like not even doing these PYQs. The function of these PYQs is to understand why anything is happening, why it is the answer and the other one is not. So here, due to the minus I effect, the nitrogen's electrons will be attracted by oxygen and hence will be less available for donation. So the most available will be second one, right? Because second one, the electrons are not participating in any resonance, they are readily available. The second will be more basic, then followed by the first one, then followed by your third one, and your fourth will be least basic because they will not at all donate. They are participating in aromaticity. So I will not donate my electrons at all. So this is the order that is followed. Second, first, third and fourth. Okay, this is the order that is followed. Understood? Next question. Which of the following compounds will show highest dipole moment? Once again, we've discussed, right? Dipole moment. Look at this compound. This is an exo bond. So this exo bond has to break. This oxygen will take away electrons. It will become positive. This will get a positive charge. This becomes a 2 pi electron system, which is aromatic. Hence, it will show the highest dipole moment because after becoming a dipole, after getting a positive and a negative charge, I'm actually becoming aromatic. So I will definitely show the highest dipole moment over here. And none of these other things are aromatic. Why? Because this is obviously sp3 hybridized, cannot be aromatic. Once again, look at these compounds. Even if I give its electrons to here, give the electrons to here, so this will get a positive charge. This will get a positive charge, this gets a negative charge, this gets a negative charge. Now this becomes a 4 pi electron system, which is anti-aromatic system, which is very, very unstable, right? Very, very unstable. Hence, it will never ever form. Never ever form. Look at this compound over here. Once again, this compound, even if it goes over here, these two atoms are actually sp3 hybridized. Right? These two atoms are actually sp3 hybridized. Right? So, once again, so they therefore cannot compete against aromaticity. Aromatic compounds are more stable. As soon as I'm converting into a dipole, two poles, I'm becoming aromatic. Hence, I will show the highest dipole moment. This is from the 2018 question, and then from then onwards has been asked plethora of times in your exam, right? Right. Next question, we've already done this basicity order. The same thing we've already done, does not contribute to basicity. We've done a similar question, right? So once again, it was asked in 2016 as well, as we're doing almost all the PYQs asked every year, right? So we've already done this. I expect everyone to know the answer. Next question is, among the following compounds, increasing order of the basic strength is. So I believe such questions you can perform on your own. We've already discussed the basic strength, acidic strength so much. So these questions you can definitely take it as homework, and because these are PYQs, you'll get the answer anywhere as well, right? So you can definitely try these questions. Next is another, we've already done this question, right? We've done this question. Next is, which of the following compound is most reactive to an aqueous solution of sodium carbonate? This is a direct rip-off from your JEE Advanced. Once again, this is a 2018 question, direct rip-off from your JEE Advanced question. Which of the following compounds is most reactive to an aqueous solution of sodium carbonate? What is sodium carbonate? It is Na2CO3. What is the function of sodium carbonate? Ma'am, it is a base. What kind of base? Weak base. So what is the function of base? To abstract hydrogen. See, if I'm a weak base, I can only take up that H plus. I'm a base, I have to take up proton, right? What is the function of base? To abstract proton. I've already established this. The function of base is to abstract. Always remember this thing, abstract proton or the H plus ion, right? So here, because it is a weak base, it can only abstract that H plus, that after taking the H plus away, that H plus is very, it can only take away H plus from very strong acids, Look at these compounds. Where can you find a very, very strong acid? After looking at these compounds, I can definitely see, look at the A option. In A option, I'm drawing the A option over here. This is the A option. If the H plus is removed from here, what is left behind is a negative charge, right? So this negative charge can actually, after this negative charge is there, can you see after this cycloalkane gets a negative charge, this becomes actually 4 pi electron system, which means it is becoming anti-aromatic. After losing H plus, I'm becoming anti-aromatic. Hence, I will not give away H plus at any cost, because otherwise there is I'm becoming very unstable, right? I'm becoming anti-aromatic. But look at the C option. In the C option, if it gives away H plus from here, what is left behind is a negative charge. This negative charge, after getting the negative charge, this is a cyclic compound, right? All the atoms are conjugated, yes. This is a planar compound, yes. The fourth option is, in this compound, how many electrons are there? 1, 2, 3, 4, 5, 6. Can everyone see? This is becoming a 6 pi electron system. So can you see? As soon as I lose H plus, I'm becoming aromatic system. I'm becoming a 6 pi electron system, which means I'm becoming a aromatic system, which means I'm becoming very stable. So I am a very strong acid, because I want someone to take away my H plus easily, so that I become very stable, right? So this is a very, what do you say, acidic compound, because, and with the base, obviously an acid reacts. With the base, always an acid reacts. With the acid, always a base reacts. So which of the following compounds is most reactive? So the C will be most reactive, because sodium carbonate is a base, and hence an acid will react with it. This is a very strong acid, right? Understood? Moving forward, the increasing order of basicity of the following intermediates from weak to strong is. First say, you have to tell me the order of basicity. What is basicity? The ability to donate electrons. Remember this thing, right? So here can you see? This is a negative charge over here. This negative charge, is right next to this plus I atom attached, this plus I group and this plus I group. So this negative charge is actually increased by more plus I groups attached. Hence this negative charge is so much more, right? So here what is happening? This is very basic, because if I already have a negative charge, you're increasing more charge on me. Hence I have much more negative charge. Hence I can easily donate the negative charge. So this is very basic species. Look at the B option. Here, this is a negative charge followed by a single bond, then a double bond. Hence, this negative charge is actually participating in resonance. Hence, it is not as readily available to donate, right? Not as readily available to donate. Look at this option. In this carbon is actually sp hybridized, right? This carbocation is actually sp hybridized. What did I teach you about sp hybridization? They are more electronegative. As the hybridization becomes from sp3 to sp2 to sp, the electronegativity increases. And as the electronegativity increases, it means what? It will keep the electrons to itself. As I told you, more electronegative the atom, less is its basicity. I'm writing it here. More electronegativity, less basicity. Less basicity, because it is not able to donate. If I am more electronegative, I will keep the electrons to myself. I will not donate them. So this is not as good donating group. Next is your CH3 minus. CH3 minus is a basic methyl ion. It can donate, because it is not stable. It can donate its atoms. Then it is your Cn minus group. Cn minus, once again, the C triple bond N, and a negative charge is actually on the carbon atom, right? So it can also easily donate the electrons, right? So Cn minus, once again, can donate the electrons, right? So it can act as a base, right? So remember one thing, as HCN is a very good acid, because the Cn ion here, the C triple bond N, and here is the 1, 2, 3, 4, 5, and here is the 6. Here is a negative charge, right? This is the structure of a, so here the negative charge can actually, here the negative charge is actually attached to this nitrogen atom, right? So here once again, it is not as great of a donating group. So these are all the effects that we can see over here. So as you can see, we can just check the options and write down the answer. The most basic is definitely the first group, right? So there is just one option related to that. The most basic group, because it is able to very easily donate the electrons, right? Because it has so much of plus I effect. So first is the most basic group, followed by your second. Why? Because in second, what is happening? Resonance is happening, but still it can donate the electrons. Followed by the fourth option, which is a CH3 minus. It is a good group. Followed by your third option, which is this, and followed by a fifth option. So this is the least basic group, Cn minus. Least basic group. It will keep the electrons towards itself. It will not easily donate. So this is the correct option. First will easily donate, followed by your second, because even after it is forming a resonating structure, it is once again gaining a negative charge like this. This is CH2, and here it is once again CH2, and here it is a minus, right? So once again, even after forming a resonating structure, once again the carbon is getting a negative charge, है ना? So that negative charge can be donated even in the resonating structure. So even after forming the resonating structure, the negative charge can be donated. So therefore it is a good donation power. Then followed by your CH3 minus, again it can donate. Then followed by your this sp hybridized carbon, and then followed by your this C. If I have to compare C triple bond C and C triple bond N, actually nitrogen is what kind of group? It is a more electronegative group. So it will attract more electrons to itself. Hence it is not able to easily donate the electrons as compared to whenever a carbon is attached to another carbon. So this one can easily donate electrons as compared to a C triple bond N. So C triple bond N is the least basic compound, right? Next question. The correct order of acidic character of the following is. So you have to tell me the acidic character of the following. Once again, for checking the acidic character, what you have to check? Which easily gives away H plus. So I am just removing H plus from here, H plus from here, H plus from here, and H plus from here. Now look at all these options. Can you see? Second, third and fourth options are actually carboxylic acid, while the first option is a alcohol. Now if I compare the acidity order, carboxylic acid, as the name suggests, will be more acidic than a phenol group. Always remember that. These will be more acidic. So first of all, I know which one is the least acidic. So your first compound is definitely the least acidic compound, because it is an alcohol or a phenol. I do not have to look for any other thing. Now I have to compare the acidity between these three. Now I have to, before comparing the acidity, I have to look for the stability of this negative charge, right? Negative charge formed. Now bacha, can you see the NO2 group attached over here is an electron withdrawing group. Hence this negative charge is stabilized by the electron withdrawing group. Hence this is the most acidic. This CH3 group actually shows a plus I effect. If I'm already negative, you're giving me electrons, you're making me more unstable. Hence this is least acidic. So the most acidic compound is actually your second compound, followed by your third compound, right? Followed by your fourth compound, followed by your second compound, right? So this is the acidity order followed. The second is more acidic because it is attached to electron withdrawing group, followed by your third, fourth, and then first compound. First, because it's a phenol, it will be even lesser acidic compound, right? Next, we've already done this question, so we are skipping this. Next question is, which of the following is the strongest base? See, so many questions are asked. This is from the PYQ of 2000. I just wanted to show you that even from 2000, similar questions have been getting asked in your JEE Mains exam, right? So look at this question. The first option is, I'm drawing all the options over here. The very first option is actually an aniline. So I'm drawing the aniline over here. The second option is a para-nitroaniline. So I'm also drawing the para-nitroaniline for you. This is the aniline group. This is a para-nitroaniline group, right? Next is your meta-nitroaniline group. Next is your meta-nitroaniline aniline group. This is the NH2 group, and at the meta position there is the NO2 group. The third option is just your this one, primary amine. This is just your CH2NH2 group. And they have asked you to actually tell me which one is the strongest base. So as I know, in all these options, in the option number A, in the option number B, in the option number C, and in the option number D, can you see some similarities? So there is just one different molecule present. Can you see the D option? In D, in here, in all the other rest of the options, this NH2 is actually participating in resonance, hence these electrons are not readily available. What is basicity? The electrons should be readily available to donate. These electrons are participating in resonance, hence not easily available to donate. Similarly, these electrons once again participating in resonance, not available to donate. These electrons participating in resonance, not easily available to donate. While these electrons are not participating in resonance, available to donate, also attached to a plus I effect, increasing the electron density, hence will be the most basic. So I'm just writing that D will be the most basic over here. Now I have to compare the basicity of A, B and C. Now see, in the B option there is a nitro group at the para position. At the para position, the nitro group shows two kinds of effects, which is minus R effect and minus I effect. What it is doing? It is withdrawing. It is actually an electron withdrawing group. So due to resonance, it is also drawing electrons. Due to inductive effect, it is also withdrawing electrons. Now look at the C option. Here the nitro group is at the meta position, right, with respect to the aniline group. So here the nitro group will just have the minus I effect and no what do you say, minus R effect. Resonance effect is not applicable at the meta position. That's what I'm teaching you. There no plus R or no minus R, no matter the direction, positive or negative. No resonance effect is applicable on the meta position. So here it is just showing the minus I effect, the electron withdrawing effect through the inductive effect, right? Now you have to compare the basicity order. So the most basic compound here, most basic it which can donate electrons very easily. So can you see, out of these, A can donate electrons very easily. So A will be a better base, followed by your C compound, followed by your B compound. So this is the final order, DACB. D is the best base, followed by your A compound because it is just showing resonance. Here in the C option, there is resonance and also an electron withdrawing minus inductive effect. So the electrons even become lesser to donate. Here even least electrons can be available for donation, right? Next question is here. We've already done a similar question related to this, right? The correct order of basicities of the following compound is. So what I'm trying to teach you is, this is once again, look at the PYQ. This is from the 2001 PYQ, right? So what I'm trying to teach you is, from these past years, similar questions are asked. So if you wanted to make your topic strong, you must definitely do these PYQs because similar questions are asked even after 10 to 20 years of these exam to be conducted, right? 2000 was like 20 years back, even more than 20 years back, right? The correct order of basicity of the following compounds are, look at this. Here the nitrogen has a lone pair, here it again has a lone pair, right? So it has two nitrogens present on it. Remember this thing. Look at this nitrogen. This nitrogen once again has a lone pair of electrons. This nitrogen also has a lone pair of electrons. Look at this. This is the amide. This is CH3, C double bond O, NH2, right? So, bacha, this is not a good base because what is happening? The electrons after showing resonance. This is a amide group and after showing resonance CO minus it is becoming and it is becoming NH2 here the plus sign is coming. So this negative charge or the extra pair of electrons are actually coming on oxygen, which is not a good donor because it is more electronegative. That's what I taught you, right? Oxygen is more electronegative, so it will not readily donate electrons. So it is the weakest base over here, right? It is the weakest base. Now here they are trying to compare you between the ethyl and CH3 whole twice NH groups, right? So here we are going to use the order that we actually learn in the amines chapter, right? In the amines chapter, you have this order right in your NCERT where they've written which one is more basic. And once again, let me tell you, because this has 2 nitrogens over here, this will definitely be more basic, right? So the first will be more, so you have to compare between these two options, which is B and D. So between B and D, you have to compare. So first will definitely be more basic because it has 2 nitrogens, and the least basic will definitely be the fourth option, right? So the B and D options seem close enough. Rest you have to compare between the option number 2 and option number 3, which you actually learn in your amines chapter. Like here, once again, if this order is asked in what? If this order is asked in your exam, once again, you have to check for the amines chapter what kind of order they've given you in your NCERT. Rest we've already discussed how to write the answer, right? So please consult the NCERT which one is more basic amongst these two, because I also keep on forgetting between these two things, right? It is definitely in your amines chapter NCERT, definitely check it out. Rest of the things are explained over here. Perfect. Next question, look at over here. 2002 question has the smallest dissociation constant. Smallest dissociation constant means what? Which is the, see, which the acids which are much more strong will have high dissociation constant. So weak acids will have small dissociation constant. So you just have to go with the wordings of the JEE Bala. Okay? So the JEE papers are created in such a manner to play with the words, but you don't have to get confused. Understand this thing. Which one will have the smallest dissociation constant? Smallest dissociation means which one will be the weakest acid, right? So you have to tell me which one will be the weak acid. You just have to tell that. Which one will be the weak acid? Smaller dissociation constant, which one will be the weak acid? We've already discussed the acidity and basicity order even before as well, right? Next question. Arrange the order in order of increasing acidic strength. Once again, acidic strength question from your 2004, right? So see, I have tried to discuss each and every kind of questions over here. So let us just do this very last question, because I think acidity, basicity, order, we've already covered most part of it, है ना? We've already covered most part of the questions over here, right? So let us take this as the very last question. Arrange in order of increasing acidic strength. Acidic strength means what? Which easily gives away H plus. We know, ma'am, this is an acid. So this is going to be the most acidic. We've already discussed COH is the acid. Definitely will be the most acidic. So X will be the most acidic. So now I just have to compare between the A and the C option. X will definitely be most acidic because it is an acid. Now I have to compare between NH3 plus and here NH3 plus. Now can you see here NH3 plus is actually, this is a positive charge, right? NH3 plus here is a positive charge and it is right next to a electron withdrawing group like a COO minus group, right? CO, what is an acid group? So acid group looks like this, C double bond OO minus group. And right next to it you have attached a NH3 plus charge, right? So can you see that this positive is right next to, no, it is not right next to this. Let me draw it carefully. This is actually a NH3 plus and here it is like this, and here there is a C double bond O minus group, right? Now here this positive charge is definitely not participating in the resonance. Now if this positive charge goes away, what will it become, right? If this positive charge goes away, H plus, this will become a normal NH3 ion with a lone pair of electrons, right? And similarly, if this H plus ion moves away, this will definitely become a NH2 ion once again. Now, bacha, which one will be the most acidic, which means which will easily give away the H plus ion? So, understand this thing. This is a electron withdrawing group. So, whenever there is a electron withdrawing group attached, right, which means what? That right next to it, that hydrogen actually becomes a more acidic hydrogen, which I've already discussed, right? So, this hydrogen will actually become more acidic. So Z will be more acidic than your Y, right? Because it is a electron withdrawing group. What kind of group this is? This is a electron withdrawing group. And what happens right next to the electron withdrawing group? That the hydrogens next to it become more acidic in nature, which I've already established. So therefore, A option seems to be a better match for this. Next question is, once again, this is a 2000 question we have already discussed, which is more basic than this. So we've already discussed, because this is a C minus ion, this is once again a C minus ion. This negative charge is on a sp2 hybridized carbon. This is on a sp hybridized carbon, and we know, ma'am, sp hybridized carbon is more electronegative, hence it will not give away the negative charge easily. But this one will definitely give away the negative charge easily because it is lesser electronegative. So this is more basic. So this is more basic. It is more basic due to less electronegativity. Simple. Due to less electronegativity, it is more and more basic. Right? I hope you enjoyed today's session. We have done approximately a lot of questions, as we had hoped to do in like a 3-hour marathon session. We'll continue doing more such sessions. Make sure to subscribe to the channel if you're new over here. And if you liked the content, if you have any doubts, if you have any complaints regarding any question, please do let me know in the comment section below so that we can sort it out together. Okay? If you have any doubts, it means that your concept or your anything is going wrong, or even my concept can go wrong somewhere. So you can correct me, or the other thing is I can correct you if you are wrong, right? It works both ways. Make sure you are writing all your doubts in the comment section below, because if you are not, it means what? If you're not writing, it means it will never be corrected anytime, any soon. If you think my answer is wrong, please let me know so that we can actually correct your, because at this point of time, I can definitely guarantee that my answers will be much more correct than yours, right? And I've always seen that students have lots and lots of doubts when it comes to their organic chemistry, because they have learned all ulta-pulta things from everywhere, and whenever they're solving questions, they're trying to apply that ulta-pulta knowledge. So you don't have to do that. We don't have to do that. We have to learn what is actually the correct answer, what are the actual correct ways to do it. So please leave a comment and make sure you're tuned in for more such videos, and let me know what else do you require, what other kind of MCQs do you require for me, because I've already planned another session which will definitely be from your hydrocarbons chapter. We'll do the very next chapter, or you can again follow the series for more such PYQs, top 100 PYQs before your JEE mains exam. Thank you so much for watching, and I'll see you in the next video. Bye-bye.